The universe is a vast, awe-inspiring place, filled with mysteries that stretch far beyond our ability to fully comprehend. From the fiery furnaces of stars to the dense, seemingly impenetrable regions surrounding black holes, the cosmos is brimming with phenomena that continue to fascinate and baffle scientists. Yet for all that we have learned about the universe over centuries, there is so much more, still hidden from our understanding. Join us as we embark on a journey through some of the most profound and captivating mysteries of the universe. Mysteries that invite us to look deeper and question the very fabric of reality. At the core of many cosmic mysteries lies the formation of black holes, some of the most enigmatic objects in space. The creation of black holes is a process that unfolds in several different ways, all of which highlight the complexity of stellar evolution and the intricate forces that govern the cosmos. One of the most widely accepted theories regarding their formation centers around the life cycle of massive stars. Stars, much like living creatures, have a finite lifespan. As a star exhausts its nuclear fuel, it can no longer withstand the intense pressure exerted by its own gravity. This marks the beginning of a spectacular yet violent end. When a massive star reaches the end of its life, the core begins to collapse under the force of gravity, and the outer layers are violently expelled in what is known as a supernova explosion. The remnant of this explosion, a dense core, is all that remains. If the core is sufficiently massive, roughly several times the mass of our Sun, it can continue to collapse, becoming ever denser. Eventually, this collapsing mass reaches a point where it forms a black hole. This catastrophic collapse bends the fabric of space and time itself, creating a region of intense gravitational pull from which nothing can escape, not even light. The boundary surrounding this black hole, known as the event horizon, marks the point of no return, the limit beyond which anything that ventures too close is doomed to be pulled inside. There are also other ways black holes can form that don't necessarily rely on the death of a single star. For example, when two neutron stars, ultra-dense remnants of collapsed stars, collide, the immense gravitational forces can overcome the repulsive forces between particles, leading to the formation of a black hole. Similarly, when a neutron star accumulates enough mass from a nearby companion star, it can surpass a critical threshold, collapsing into a black hole. In addition to these processes, there are speculative theories that suggest primordial black holes, those that might have formed shortly after the Big Bang, could exist. These hypothetical black holes would have emerged from fluctuations in density in the early universe, rather than from collapsing stars. These varied mechanisms highlight not only the many ways in which black holes can form, but also the diverse environments in the universe that give rise to them. Whether born from the explosive death of a star, the collision of dense objects, or the gravitational collapse of ancient regions in the universe, each type of black hole formation gives us deeper insight into the nature of cosmic evolution and the forces that govern the universe. Within the realm of black holes, there are two primary categories: stellar black holes and supermassive black holes. Despite their shared name, these two types of black holes are vastly different in their origins, sizes, and roles within the cosmos. Stellar black holes form when massive stars run out of fuel and collapse under their own gravity, a process that typically leads to the formation of black holes several times more massive than our Sun. These black holes are relatively small on a cosmic scale and typically reside in stellar remnants, the final product of a star's life cycle. In stark contrast, supermassive black holes reside at the centers of most galaxies, including our own Milky Way. These gargantuan black holes can contain millions, if not billions, of times the mass of our Sun. The exact mechanism behind their formation remains one of the most intriguing mysteries in astrophysics. Scientists have proposed several theories suggesting that supermassive black holes may have formed from the merging of many smaller black holes over billions of years, or through the accumulation of vast amounts of gas and dust over time. As they grow, these supermassive black holes exert a profound influence on their galaxies, regulating star formation and shaping the structure of their surrounding environments. One of the most fascinating features of supermassive black holes is their ability to affect the entire galactic ecosystem. As matter spirals toward a black hole, it forms a disk of superheated material known as an accretion disk. This disk radiates immense amounts of energy, including X-rays, which can be detected by specialized telescopes. These powerful emissions can regulate star formation in the galaxy by triggering the expulsion of gas and dust, shaping the overall evolution of the galaxy over vast timescales. While stellar black holes are the remnants of individual stars, supermassive black holes are colossal entities at the very heart of galaxies, playing a significant role in the ongoing evolution of the universe. Understanding the differences between these two types of black holes helps illuminate the structure and behavior of galaxies and the larger cosmic tapestry that connects everything in the universe. At the heart of any black hole lies the event horizon, a boundary that marks the point beyond which nothing, no matter no radiation, not even light, can escape. To fully grasp the significance of this boundary, one must imagine standing on the edge of a cliff, staring into an abyss. Once you leap off, there is no turning back. Similarly, once an object crosses the event horizon, it enters a region of space where gravitational forces are so extreme that escape becomes impossible. This boundary represents the threshold between the observable universe and the hidden depths of a black hole, a region where conventional physics as we know it begins to break down. To an observer watching from a distance, an object that falls into a black hole appears to slow down as it approaches the event horizon. The closer it gets, the more time appears to stretch, and to the outside observer, it seems as if the object freezes in place. This effect, known as time dilation, creates the illusion that time itself slows down at the event horizon, even though the object falling in continues its descent into the black hole, unaware of the external observation. The event horizon, in essence, represents a fundamental shift in our understanding of space-time, a threshold that challenges the very nature of reality itself. Understanding the event horizon is crucial because it forces us to reconsider the laws of physics and the structure of the universe. What happens to matter and energy once they cross this boundary? What can we learn from the mysteries of space-time that exist in the black hole's depths? These questions remain open, and they invite us to delve further into the unknown, in search of answers to some of the most profound questions about the nature of the universe. Despite the inherent challenges posed by black holes, most notably their invisibility, scientists have developed innovative methods to study these objects and gain insights into their properties. One of the primary techniques involves observing the light emitted by nearby stars and gas clouds. When matter is drawn toward a black hole, it forms an accretion disk, a rotating mass of hot material that radiates intense energy, particularly in the form of X-rays. By using specialized telescopes that can detect this high-energy radiation, astronomers are able to infer the presence of black holes and study their characteristics. Another technique that has proven invaluable in studying black holes is gravitational wave detection. When two black holes merge, they create ripples in the fabric of space-time, similar to the way a stone creates ripples on the surface of a pond. These gravitational waves carry information about the merging black holes, such as their masses, spins, and other properties. Instruments like the Laser Interferometer Gravitational Wave Observatory, LIGO, are designed to detect these tiny distortions in space-time, providing scientists with a new way to study black holes and their interactions. By piecing together observations from multiple sources, light, X-rays, gravitational waves, scientists are gradually uncovering the mysteries of black holes. As technology advances and our understanding of the universe deepens, we may one day unlock the full story of these fascinating cosmic entities and reveal the secrets hidden within their depths. Until then, the journey into the heart of the black hole remains one of the most exciting and mysterious frontiers of modern science. The Event Horizon Telescope has become a pivotal tool in our exploration of the cosmos, capturing breathtaking images that allow us to peer into the very heart of some of the universe's most mysterious phenomena. Among its most awe-inspiring revelations is the visual representation of black holes, showing the eerie and powerful shadows they cast against the hot, glowing gas that surrounds them. The first image of the black hole at the center of our own galaxy is a striking example where the sharp contrast between the black void and its luminous surroundings offers a profound glimpse into how these celestial giants interact with the matter and energy around them. These extraordinary observations have transformed our understanding of black holes. Rather than being mere empty voids consuming all in their path, black holes are now understood as powerful, dynamic forces in the universe. They play a crucial role in the cosmic ballet of stars, gas, and matter, influencing their motions and interactions in ways previously unimaginable. With each new image, new data, and new insight, scientists continue to piece together a more complete picture of these enigmatic objects, slowly unraveling the mysteries surrounding their formation, behavior, and role in the evolution of galaxies and the very structure of the universe itself. Perhaps one of the most groundbreaking ideas to emerge from this research is the concept of Hawking radiation, a revolutionary theory proposed by the brilliant physicist Stephen Hawking. At first glance, black holes might seem to be nothing more than cosmic vacuum cleaners, sucking in everything, even light, with an irreversible pull. The idea that a black hole could somehow emit radiation seems paradoxical, yet Hawking's work has shown that, in fact, black holes can indeed release energy, thanks to quantum effects occurring near their event horizons. To understand this, it helps to imagine the event horizon as the boundary where the known laws of physics begin to break down, and where the strange world of quantum mechanics comes into play. In this quantum realm, particles continuously pop in and out of existence in what are called virtual particle pairs. Normally, these pairs annihilate each other almost immediately after appearing. But at the very edge of a black hole, something extraordinary can happen. One of these virtual particles may be drawn into the black hole while the other escapes into space. The escaping particle manifests as radiation, and this radiation is what we refer to as Hawking radiation. The particle that falls into the black hole has an unexpected effect. It essentially reduces the mass of the black hole. This process sets in motion a slow but inevitable process of mass loss, akin to a candle burning down over time as it consumes its wax. As a result, black holes are not permanent fixtures in the universe. Over incredibly vast stretches of time, they can lose energy and eventually evaporate completely. This discovery has profound implications. If black holes can indeed evaporate over time, what happens to the information that once fell into them? This question, known as the information paradox, has been the subject of intense debate in the field of physics. If black holes disappear through the emission of Hawking radiation, what becomes of the matter and energy that they absorbed? This riddle has pushed the boundaries of our understanding, forcing physicists to rethink the very nature of space, time, and information itself. Hawking radiation, then, is not just a theoretical insight into the behavior of black holes, it is a key to unlocking the deepest mysteries of the universe, bridging the gap between the seemingly incompatible realms of gravity and quantum mechanics, and offering clues to the ultimate fate of the cosmos. In tandem with the study of black holes, another profound mystery looms over our understanding of the universe: the existence of dark matter. The evidence for dark matter is both diverse and compelling, and it has been accumulating for decades, gradually painting a picture of a universe far more complex than we could have imagined. One of the strongest pieces of evidence comes from the way galaxies rotate. Observations of stars in distant regions of galaxies reveal something unexpected. The stars at the outer edges of galaxies move at speeds so high that without additional unseen mass to hold them in place, the galaxies should tear themselves apart. Yet, despite these high velocities, the galaxies remain intact. This mysterious force that prevents their disintegration is attributed to dark matter, an invisible substance that exerts gravitational influence but is completely undetectable by any direct observation. Another striking piece of evidence comes from gravitational lensing, a phenomenon that occurs when the light from distant objects passes by massive celestial bodies, such as galaxy clusters. The intense gravitational field of these objects bends the light, distorting the view of the objects behind them. This bending provides a means for scientists to estimate the total mass of the foreground objects. The surprising result is that visible matter alone cannot account for the amount of bending observed. This discrepancy suggests that a substantial amount of unseen mass, dark matter, is present, exerting its gravitational pull. Additionally, the cosmic microwave background, CMB, the faint afterglow of the Big Bang, holds crucial clues. The CMB shows slight fluctuations in temperature and density, which reveal important information about the distribution of matter in the early universe. These patterns align remarkably well with the predictions that include dark matter, which plays a vital role in the formation of large-scale structures like galaxies and clusters. Finally, numerical simulations of the universe's formation consistently require dark matter to explain the distribution of galaxies and clusters as we observe them today. Without dark matter, these simulations fail to reproduce the structures we see in the actual universe. Taken together, these diverse strands of evidence, galactic rotation curves, gravitational lensing, the cosmic microwave background, and computer simulations, build a powerful case for the existence of dark matter. However, despite decades of research, its true nature remains elusive. We know it must exist, but we have yet to understand what it is made of or how it behaves on a fundamental level. Even more mysterious is dark energy, the enigmatic force that seems to be driving the accelerated expansion of the universe. For much of the 20th century, scientists believed the expansion of the universe was slowing down due to the gravitational pull of matter. However, in the late 1990s, observations of distant supernovae revealed something astonishing. The universe's expansion is not slowing down, it is accelerating. This discovery led to the realization that some unknown force, now dubbed dark energy, must be pushing the universe apart. Imagine the universe as a balloon being inflated. As the balloon expands, every point on its surface moves away from every other point. This is similar to how the universe stretches, with galaxies moving away from one another as space itself expands. What's more perplexing is that this expansion is accelerating, not slowing down. The cause of this accelerated expansion is attributed to dark energy, a force that remains completely mysterious despite its profound influence on the universe's large-scale structure. Dark energy's discovery has reshaped our understanding of the cosmos, suggesting that the majority of the universe is made up of forces and substances that remain invisible and poorly understood. But, like the search for dark matter, the quest to understand dark energy is only just beginning. Together, dark matter and dark energy represent two of the greatest frontiers in modern physics, challenging our deepest assumptions about the nature of reality itself. Gravitational pull, which once held the universe together, is now being steadily overcome by a force that is both mysterious and incredibly powerful: dark energy. This enigmatic form of energy, which makes up about 68% of the universe, is a driving force that exerts a sort of pressure, pushing outward, making galaxies and cosmic structures expand at an ever-increasing rate. Scientists have only recently begun to observe the effects of this force, and they've done so through the study of distant supernovae, exploding stars that shine with extraordinary brightness. By measuring the light from these supernovae, researchers have discovered something astonishing. These stars are farther away than expected, a phenomenon that contradicts the long-held belief that the expansion of the universe was slowing down. Instead, the data reveals that the universe is expanding at an accelerating pace, a process powered by the mysterious dark energy. Though dark energy remains one of the greatest unknowns in modern physics, its effects are undeniable and profound. It is a key player in shaping the large-scale structure of the universe, influencing the movement of galaxies, and ultimately determining the fate of everything within it. The forces of dark energy interact with the very fabric of space-time itself, stretching it, pushing the cosmos outward, and creating an ever-widening universe. This forces scientists to rethink the ultimate fate of the cosmos. Will it continue expanding forever, or could dark energy eventually give way to gravity, leading to a reversal, a contraction of the universe? These scenarios are all part of the ongoing puzzle, and understanding dark energy is key to predicting how the universe will evolve over billions of years. For now, dark energy remains an unstoppable force, pulling galaxies further apart, creating a future where the spaces between them grow ever larger, distant, and isolated. Parallel to the puzzle of dark energy, there is another fundamental mystery lurking in the cosmos: dark matter. This invisible substance, which makes up about 27% of the universe, is one of the most elusive components in astrophysics. Its existence is inferred not through direct observation, but through its gravitational effects. Unlike dark energy, dark matter does not have an outward push or influence. Instead, it has mass, and that mass affects the movement of galaxies and galaxy clusters. For example, when scientists measure the speed of stars orbiting the edges of galaxies, they observe something strange. These stars are moving much faster than they should, given the visible matter around them. If only the stars, gas, and dust of the galaxy were present, the outer stars would be moving at a much slower pace. This extra speed, which cannot be explained by the gravitational pull of the visible matter alone, is attributed to the presence of dark matter, whose mass exerts an invisible gravitational force on these stars, keeping them in orbit. Detecting dark matter is one of the most difficult challenges in modern science. This is largely due to the fact that dark matter does not emit, absorb, or reflect light, making it completely invisible to traditional telescopes and instruments. However, scientists have developed several innovative techniques to study dark matter. One of the most effective methods is through its gravitational effects on ordinary matter. For instance, gravitational lensing, the bending of light as it passes through massive objects, can reveal the presence of unseen mass. When light from distant galaxies passes near a cluster of dark matter, the light bends in a way that reveals the gravitational influence of the dark matter, even though it remains invisible to the eye. This provides an indirect but powerful way to study dark matter's distribution across the universe. Another method that scientists use to study dark matter involves particle detectors located deep underground or in remote locations. These detectors are designed to spot rare interactions between dark matter particles and regular matter. Since dark matter does not interact with light, it's incredibly difficult to detect. But if a dark matter particle does collide with a regular atom, the resulting energy may create a signal that can be measured. These experiments are akin to trying to detect the faintest trace of a shadow in a pitch-black room. For now, scientists are still trying to capture that elusive signal, hoping that these experiments will one day yield the first direct evidence of dark matter. In addition to particle detectors and gravitational studies, astronomers also conduct large-scale cosmic surveys to study the distribution of galaxies, gas, and other structures throughout the universe. These surveys can reveal the underlying gravitational influence of dark matter on large-scale cosmic formations, and they offer a window into how galaxies cluster together, providing crucial clues about dark matter's role in the formation of these structures. Together, these techniques form a multifaceted approach to studying one of the universe's greatest mysteries. By piecing together clues from different methods, scientists are slowly uncovering the nature of dark matter, which is essential to our understanding of how the universe is constructed and how it functions on both the smallest and largest scales. Both dark matter and dark energy challenge our current understanding of physics, especially in terms of how they influence the cosmos. While visible matter, the stars, planets, and galaxies we see, makes up only a small fraction of the universe's total mass, these two unknown components make up nearly 95% of the cosmos. Dark matter, in particular, presents a major challenge to our understanding of gravity and the way galaxies rotate. The behavior of galaxies, especially how they spin, suggests that their mass is distributed in a way that we cannot directly observe. This is akin to a basketball that wobbles when spun due to the presence of uneven weight distribution, except in this case, the weight is invisible. These findings strongly indicate the existence of dark matter, and scientists are racing to find more evidence to confirm its properties and role in the universe. Dark energy, on the other hand, is even more perplexing. Rather than being a form of mass, dark energy appears to be a force that is pushing galaxies apart. When astronomers observe distant galaxies, they see that they are moving away from us at an ever-increasing speed. This was a surprising discovery because, based on earlier models, scientists had expected that the gravitational pull between galaxies would slow down the rate of expansion. Instead, dark energy is acting like a cosmic force, pushing galaxies apart, counteracting the pull of gravity and accelerating the expansion of the universe. This behavior can be visualized by imagining a balloon being inflated. As air is blown into it, every point on the surface of the balloon moves away from every other point. In the same way, dark energy is causing space itself to expand, pushing galaxies away from one another, and altering the very fabric of the universe. Together, dark matter and dark energy suggest that our understanding of the universe is far from complete. Current physical theories, including those concerning gravity and fundamental forces, are being tested and challenged by these mysterious phenomena. It is likely that the next breakthroughs in physics will come from studying dark matter and dark energy, and unraveling their true nature could reshape our entire understanding of how the universe works. These cosmic puzzles are not just academic exercises, they have real implications for the future of the universe itself. As dark energy continues to drive the accelerated expansion of the universe, cosmologists suggest that we could be headed toward a scenario known as the Big Freeze. In this scenario, galaxies will move so far apart that over billions of years, they will become isolated from one another. The universe will continue expanding, growing colder and darker until it becomes a desolate, empty place. This may sound like an improbable ending, but it is one that is increasingly supported by current models of cosmic evolution. The study of dark energy and dark matter is also connected to one of the most significant discoveries in the history of cosmology, the Big Bang theory. The evidence for the Big Bang is compelling and continues to grow. Perhaps the most significant piece of evidence is the discovery of cosmic microwave background radiation. This faint glow, detectable across the entire sky, is thought to be the leftover heat from the early universe when it was still hot and dense. As the universe expanded, this radiation cooled and spread out, and its uniformity across the sky supports the idea that the universe began from a single, highly energetic point. Another piece of evidence supporting the Big Bang theory comes from the observed expansion of the universe. When astronomers look at distant galaxies, they see that they are moving away from us. This observation, first made by Edwin Hubble in the 1920s, led to the conclusion that the universe is expanding. If we trace the movement of these galaxies backward in time, they all seem to converge at a single point, suggesting that the universe began in an explosive event, what we now call the Big Bang. These observations, along with the discovery of cosmic microwave background radiation, provide strong support for the idea that the universe had a beginning and has been expanding ever since. In conclusion, while dark matter and dark energy remain some of the most profound mysteries in science, they are key to understanding the universe's past, present, and future. As we continue to study these elusive components, we move closer to a deeper understanding of the cosmos and its ultimate fate. The journey is just beginning, and the answers we find may forever change how we perceive the universe and our place within it. Following the Big Bang, an extraordinary transformation began to unfold across the cosmos. In its infancy, the universe was a hot, dense, and chaotic place, conditions that laid the groundwork for everything we observe today. Among the most compelling pieces of evidence supporting the Big Bang theory is the prevalence of light elements, hydrogen, helium, and trace amounts of lithium, that were created in the early moments following the explosion. These light elements, which formed in the very first stages of the universe, are scattered throughout the cosmos. Scientists, using the principles of Big Bang nucleosynthesis, can predict the amounts of these elements, and when they compare these predictions with actual measurements from the universe, the results show a stunning level of agreement. This alignment provides powerful validation for the Big Bang theory, further reinforcing the idea that the universe began in a fiery, dense state before expanding into what we know today. Yet, this evidence does not stop there. Large-scale structure observations offer another crucial layer of support for the Big Bang framework. By examining the distribution of galaxies across vast stretches of space, scientists have been able to uncover a pattern that mirrors what we would expect from the early universe. The distribution is not random, but instead reflects the expansion and growth of cosmic structures that began as tiny, minute fluctuations in the density of matter during the universe's infancy. These fluctuations eventually led to the formation of galaxies and clusters of galaxies, all of which have continued to evolve over billions of years. The Big Bang Theory ties all these observations together, painting a coherent picture of the universe's birth and its gradual development. At the heart of this story is the cosmic microwave background, CMB, the faint afterglow that fills the universe, a lingering signature of the Big Bang itself. The CMB provides a direct window into the conditions of the early universe, acting as a time capsule from when the universe was just a fraction of a second old. In its early moments, the universe was incredibly hot and dense, and light could not travel freely. However, as it cooled and expanded, photons, particles of light, were finally able to move unimpeded. This light is what we now observe as the CMB, providing a snapshot of the universe as it began to cool, just over 13 billion years ago. The CMB is remarkably uniform across the cosmos, with temperature variations that are minuscule yet profoundly significant. These temperature fluctuations in the CMB serve as a map, revealing the density differences that would eventually lead to the formation of galaxies and other cosmic structures. By analyzing these variations, scientists can glean a wealth of information about the universe's early conditions, its rate of expansion, its composition, and even the fundamental physics that governed the universe in its infancy. The CMB is more than just a faint glow in the sky. It is a relic from the moment when atoms first formed and light began to travel freely across space. It gives us invaluable insight into the universe's evolution, allowing cosmologists to test theories about the universe's future and its ultimate fate. The CMB acts as a direct link between the universe's fiery birth and its current, vast, and structured state. It helps us understand how the universe transitioned from a hot, dense state to the expansive cosmos we inhabit today. Through the CMB, we can witness the intricate processes that shaped the universe over billions of years, offering us a deeper understanding of not only how the universe began, but how it evolved over time. Inflation theory, which proposes an exponential expansion of the universe just after the Big Bang, plays a pivotal role in explaining the universe's evolution. Imagine, if you will, the universe as a small, incredibly hot and dense balloon, roughly the size of a pinhead. In the mere fraction of a second after the Big Bang, this balloon began to expand at an incomprehensible speed, stretching rapidly in every direction. This expansion was not just the stretching of space, it was the very fabric of space itself being created. During this brief but transformative period, the universe grew from a subatomic size to about the size of a grapefruit. The implications of inflation are profound. It essentially smoothed out the universe, erasing any irregularities or inconsistencies, and making the universe remarkably uniform at large scales. It laid the groundwork for the formation of galaxies, stars, and the large-scale structures we see today. This theory provides an elegant solution to one of the major puzzles in cosmology: why the universe appears so homogeneous despite its complexity. Without inflation, the distribution of matter in the universe might have been much more chaotic, potentially leading to a very different cosmic evolution. Inflation not only explains why the universe is as we see it today, but also acts as a cosmic reset, ensuring a smoother, more predictable path for the formation of galaxies and stars. The concept of the multiverse, which extends the Big Bang Theory to include the possibility of multiple, perhaps infinite, universes, presents an even more profound expansion of our understanding of the cosmos. While the Big Bang describes the birth of our universe, its origin from a singular point, multiverse theory suggests that this event could have occurred in multiple places, with countless other universes emerging in parallel, each potentially governed by its own set of physical laws. In this vision, our universe becomes one of many, each universe potentially experiencing its own Big Bang-like expansion. Imagine the multiverse as an ocean filled with bubbles. Each bubble represents a distinct universe, formed independently yet existing side by side with countless others. Some of these bubbles may resemble our own universe, governed by similar laws of physics and containing similar forms of matter. Other bubbles, however, may be radically different, with entirely unique sets of physical laws and conditions. The idea that each universe could have its own Big Bang, leading to different outcomes, challenges our traditional view of creation. It suggests that our universe is not the singular origin of everything, but rather one piece in a much larger, more intricate puzzle of infinite possibilities. The multiverse theory invites us to rethink the very nature of reality. It raises the tantalizing possibility that our universe, while extraordinary, is only a small part of a much grander cosmic story. Our entire reality could be just one chapter in a boundless narrative stretching across infinite universes, each one unfolding its own unique history. This theory challenges the notion that our universe is the only one of its kind, expanding the scope of our inquiry into the very origins of existence. Even though the Big Bang Theory has become the cornerstone of our understanding of the universe's beginnings, there are still many mysteries that remain unresolved. For one, while we know the universe began from an incredibly hot and dense state, the exact conditions at the moment of the Big Bang remain elusive. How did the universe transition from this singularity to the expansive cosmos we observe today? This question continues to intrigue and puzzle scientists. Another enduring mystery is the nature of cosmic inflation. While the theory of inflation provides a compelling explanation for the uniformity and structure of the universe, we are still uncertain about what caused this rapid expansion and how it unfolded. What triggered inflation, and how did it influence the universe's development? These are questions that continue to drive much of the research in cosmology. As scientists work to uncover more about the origins and early moments of the universe, they hope to unlock answers that will not only clarify the Big Bang, but also deepen our understanding of the very fabric of reality itself. Moreover, the enigmatic nature of dark matter and dark energy, which together make up the vast majority of the universe's total energy density, remains one of the greatest unsolved mysteries in modern physics. Despite the remarkable efforts of theorists who have constructed a wide variety of models to explain the existence of these elusive forces, much about their fundamental properties and the exact roles they played in the aftermath of the Big Bang is still largely unknown. While dark matter is thought to account for the gravitational effects observed in galaxies and galaxy clusters, and dark energy is believed to be responsible for the accelerated expansion of the universe, the precise relationship between these dark entities and regular visible matter continues to defy our understanding of the cosmos. Adding another layer of complexity to our quest for cosmic knowledge is the matter-antimatter asymmetry, a profound conundrum that challenges our fundamental understanding of physics. According to the theory of the Big Bang, the birth of the universe should have produced equal amounts of matter and antimatter, which would have annihilated each other upon contact, leaving behind only pure energy. However, what we observe today is a universe predominantly made up of matter, with antimatter being scarce to the point of near non-existence. This imbalance has sparked intense theoretical and experimental exploration, with scientists seeking to understand why the universe seems to favor matter over antimatter, an investigation that could reveal new revolutionary insights into the very laws of nature. Furthermore, one of the most exciting and still largely unexplored areas of cosmology is the formation of the first stars and galaxies. Understanding how the first structures emerged from the nearly uniform, hot, and dense state that followed the Big Bang is a central puzzle in the study of cosmic evolution. These early processes, which saw vast clouds of gas clumping together under the influence of gravity, ultimately gave rise to the richly textured cosmos that we observe today. Yet, the exact mechanisms that allowed this initial formation of stars and galaxies remain somewhat mysterious. Gaining a clearer understanding of these processes is essential for completing our narrative of the universe's birth, offering vital clues as to how the complexity of the cosmos arose from such a simple, uniform origin. While the Big Bang provides a foundational framework for understanding the origins of the universe, it simultaneously raises a host of profound questions and mysteries, each with the potential to dramatically reshape our comprehension of the universe itself. As we continue to study these deep, unresolved enigmas, scientists are developing innovative strategies and technologies that may one day lead to breakthroughs that transform our understanding of everything, from the smallest particles to the vast, incomprehensible expanse of space. One of the most captivating quests in modern science is the search for extraterrestrial life. As we look outward, scientists are exploring both our own solar system and distant exoplanets in an effort to find evidence of life beyond Earth. In our own backyard, researchers are particularly drawn to Mars, where past evidence of liquid water suggests the planet may have once been capable of supporting life. Robotic missions equipped with specialized instruments are sent to Mars to scour its surface, analyzing soil and atmospheric samples for signs of organic compounds, the fundamental building blocks of life. The possibility that life may have once existed on Mars, or even might still be present in some microbial form, keeps this red planet a key focus of astrobiological research. In addition to Mars, the icy moons of the outer solar system, such as Europa and Enceladus, present compelling targets for the search for life. Beneath their thick, icy crusts, both moons harbor vast subsurface oceans, and scientists believe these environments could potentially support life. Spacecraft sent to these moons may one day have the ability to penetrate the icy shells and sample the water beneath, searching for microbial life or chemical signatures that could suggest the presence of life. These missions hold enormous promise, as they may uncover entirely new forms of life that thrive in places vastly different from Earth. The search for life extends far beyond our solar system. The discovery of exoplanets, planets orbiting stars outside our solar system, has opened new avenues in the search for extraterrestrial life. With the advent of powerful space telescopes, astronomers are now able to study the atmospheres of these distant worlds. When an exoplanet transits in front of its host star, light from the star filters through the planet's atmosphere, allowing scientists to analyze the composition of gases present in the air. Certain gases, such as oxygen and methane, can be indicators of biological processes, as these compounds are often associated with life. When these gases are found together, they may suggest that a planet has the conditions necessary to support life. Moreover, the search for technosignatures, artificial signals or emissions that might point to intelligent extraterrestrial civilizations, adds another exciting dimension to the search for life. Scientists are continuously scanning the cosmos for unusual radio signals or other patterns in the electromagnetic spectrum that could indicate the presence of intelligent sources. Organizations like SETI, the Search for Extraterrestrial Intelligence, are dedicated to monitoring the skies, looking for any deviation from the natural background noise of the universe that could point to technologically advanced civilizations beyond Earth. As technology advances, the search for these signatures is becoming more refined and increasingly sensitive. The integration of artificial intelligence, AI, into these efforts has further accelerated the pace of discovery. AI technologies are capable of sifting through enormous amounts of data from telescopes and space missions, identifying potential signs of life far more efficiently than traditional methods. By automating the process of detecting anomalies in large data sets, AI is helping to speed up the identification of promising leads, allowing scientists to focus their attention on the most promising signals. As these various methods converge, scientists are piecing together the puzzle of whether we are alone in the universe. Every breakthrough, whether it is the discovery of a potential biosignature or the identification of a technosignature, brings us one step closer to answering this age-old question. As we expand our understanding of life, not only as we know it on Earth, but also as it might exist elsewhere, we are redefining the boundaries of what is possible in the search for life beyond our home planet. One fascinating avenue of exploration is the study of extremophiles, organisms that thrive in some of the harshest environments on Earth. These remarkable creatures, which live in environments like deep-sea hydrothermal vents, acidic hot springs, and frozen tundras, provide valuable insights into how life might exist in extreme conditions elsewhere in the universe. The existence of extremophiles challenges our conventional thinking about what constitutes a habitable environment, suggesting that life could exist on planets or moons with conditions far harsher than those found on Earth. For instance, the discovery of extremophiles living in conditions devoid of sunlight, such as deep-sea organisms that rely on chemical energy rather than solar energy, opens up the possibility that life could exist on celestial bodies that do not receive light from their stars. Moons like Europa with its subsurface ocean and planets like Mars with its cold and arid surface become increasingly intriguing as potential habitats for life. If extremophiles can survive in such extreme environments on Earth, it stands to reason that similar organisms could potentially thrive on other worlds that might have once harbored liquid water or still maintain subsurface oceans. Moreover, understanding how extremophiles extract energy from sources other than sunlight encourages scientists to rethink traditional models of habitability. These organisms demonstrate that life does not necessarily depend on photosynthesis, the process by which plants and some microorganisms use sunlight to produce energy. This has profound implications for the search for life beyond Earth, as it expands the criteria by which we judge whether a planet or moon could host life. Life, it seems, might not require the familiar conditions we associate with habitability, and this opens up vast new frontiers for exploration. Extremophiles, in essence, serve as a biological blueprint for the resilience and adaptability of life. Their existence offers hope that even in the most unlikely environments, life may find a way to survive and thrive. With each new exploration mission to distant planets and moons, there remains the possibility that we might encounter organisms, however alien, that mirror the extraordinary tenacity and adaptability of life on Earth. Finally, the discovery of exoplanets within the so-called habitable zone, often called the Goldilocks zone, has radically expanded our understanding of the potential for life elsewhere in the universe. This zone represents the region around a star where the conditions are just right for liquid water to exist on a planet's surface, neither too hot nor too cold. Given that water is essential for life as we know it, the identification of exoplanets within this zone is particularly exciting. Each new discovery offers the tantalizing possibility that we are not alone in the universe, and that life, perhaps in forms we cannot yet imagine, may exist on distant worlds. As our telescopes improve and our exploration missions venture farther into the cosmos, the range of possible planets that could support life grows exponentially. We are no longer limited to the search for Earth-like planets alone. Instead, the universe reveals itself as a vast, diverse expanse of worlds, each with its own potential for life. Each exoplanet discovered in the habitable zone deepens our understanding of what is possible and invites us to consider the incredible diversity of planetary systems that may exist, each with the potential to host life in its own unique form. With each passing day, our knowledge of the universe expands, and the dream of discovering life beyond Earth seems ever more achievable. Moreover, studying these exoplanets reveals far more than just the possibility of alien life. It provides profound insights into the atmospheres and surface conditions that shape these distant worlds. By analyzing these exoplanets, scientists can explore their potential to support life by examining key markers such as the presence of essential elements or chemicals, carbon dioxide, nitrogen, and even organic molecules. These components are all crucial indicators that may suggest a planet's ability to harbor life. However, the importance of these discoveries transcends the mere search for extraterrestrial life. They push the boundaries of our understanding, challenging how we perceive the origins and the potential for life in diverse environments far removed from Earth. The search for life in the universe goes beyond simply finding organisms. It encourages scientists to reevaluate the very conditions that might foster life in unfamiliar and unconventional places. What if life could arise in ways that diverge dramatically from our own experiences and expectations? With advances in technology, we are continually able to gather more data, allowing us to refine our understanding of how likely it is that life could exist beyond our planet. Each exoplanet discovered within a habitable zone, an area where conditions might be suitable for life, contributes to a grand narrative of cosmic exploration, igniting both our curiosity and our hopes about humanity's place in the vast universe. But the concept of life beyond Earth presents an intriguing question. What might life on other planets actually look like? Life elsewhere could take forms and exhibit characteristics that are entirely different from what we experience on Earth. One of the most fundamental ways in which extraterrestrial life might differ from ours is how organisms obtain energy. On Earth, most life forms rely on sunlight to fuel their metabolic processes, converting it through photosynthesis. However, on a world where sunlight is scarce, like beneath the ice of Europa, one of Jupiter's moons, life could evolve to depend on chemical energy instead. Organisms in these extreme environments might breathe substances like hydrogen sulfide, much like the microbes found near deep-sea hydrothermal vents on Earth. The basic building blocks of life could also be strikingly different. While life on Earth is primarily carbon-based, other planets, with their distinct elemental compositions, might host organisms built on alternative chemistries, such as silicon. This shift could result in beings whose physical structures are unlike anything we recognize, and who might have methods of reproduction, communication, and even perception that challenge our understanding. Conditions such as atmospheric composition and gravity would further influence how these life forms evolve. On planets with higher gravity, organisms might develop more robust, stronger frames to support their weight, while those in atmospheres with thick, dense gases could evolve respiratory systems that bear little resemblance to our own. In a world where temperatures swing to extremes, either searingly hot or chillingly cold, life might rely on unique biochemical adaptations. Some organisms might produce antifreeze-like proteins to survive in freezing conditions, while others could develop heat-resistant enzymes to withstand the scorching heat. In such environments, bioluminescence, a trait seen only in a few species on Earth, could become a common adaptation on planets where sunlight is scarce, obscured by dense clouds or distant stars. Similarly, the ways in which life interacts with its environment could vary in unexpected ways. Organisms might evolve to use echolocation or even other sonar-like methods to navigate dark and foggy worlds where visibility is limited. In such places, the senses that life forms rely on could be radically different from what we know. Instead of sight or smell, perhaps creatures would rely on entirely new means of interacting with the world around them. The idea of life beyond Earth often evokes visions of creatures that resemble familiar animals, perhaps some green-skinned aliens or strange, multi-limbed beings. However, the realities of extraterrestrial life could be far more exotic, shaped by alien conditions on their home planets, planets that may have compositions and environments radically different from our own. The diversity of potential ecosystems could lead to forms of life that diverge significantly from anything we can imagine. In such a diverse universe, it's possible that life could exist in ways that are so foreign to us that we cannot even conceptualize them. The discovery of microbial life on Mars or any other celestial body would have far-reaching consequences for how we view our place in the cosmos. First and foremost, it would challenge our perspective on humanity's uniqueness in the universe. To learn that we are not alone, that life exists elsewhere, would be one of the most profound shifts in human thought. It would deepen our understanding of biology, of how life can emerge, and of the conditions that nurture it. The discovery of extraterrestrial microbes would suggest that life is not an Earth-centric anomaly, but rather a natural outcome of certain conditions that could be replicated on countless other planets throughout the universe. Such a revelation would transform our view of previously considered barren or lifeless celestial bodies. Moons and planets once thought to be sterile wastelands, such as Mars, Europa, or Enceladus, could instead harbor thriving ecosystems, even if those ecosystems are microbial. Furthermore, the study of these Martian or extraterrestrial microbes would provide invaluable insights into life's ability to adapt to extreme environments. Scientists would delve into how these organisms survive in hostile conditions, environments with harsh radiation, freezing temperatures, and limited resources. This knowledge could not only teach us about the resilience of life, but it might also inspire new biotechnologies here on Earth, such as bacteria capable of surviving in extreme conditions or producing energy from novel sources. In addition to advancing science, the discovery of alien life would ignite deep philosophical and ethical debates. How should humanity respond to the discovery of life on other planets? What responsibilities do we have toward these extraterrestrial ecosystems, particularly when it comes to protecting them from contamination by our exploration missions? As we venture further into the cosmos, we will need to establish new guidelines for planetary protection and be prepared to answer questions about the potential consequences of our actions on other worlds. If we prove that life exists beyond Earth, it would stretch the limits of scientific inquiry, pushing us to develop new technologies and methods to explore our solar system and beyond. The quest to understand the origins and variations of life would unite humanity in an unprecedented way, fostering global collaboration in space science and exploration. Such a discovery would not only alter the trajectory of science, but would deeply impact culture and philosophy, reshaping how we see ourselves in the broader context of the universe. The Milky Way galaxy, a breathtaking spiral of stars, gas, and dust, forms the very backdrop of our cosmic journey. It is a stunning, dynamic structure shaped like a vast, flattened disk, its arms spiraling outward like fingers, reaching into the depths of space. At the heart of this galactic expanse lies a supermassive black hole, an invisible yet incredibly powerful force that pulls everything in its vicinity toward it with relentless gravitational pull. It is this colossal force that shapes the destiny of stars, planets, and entire star systems within the galaxy. Our solar system resides within one of the spiral arms of the Milky Way, specifically in a region known as the Orion Arm. This arm is a minor structure located between two larger arms, the Perseus Arm and the Sagittarius Arm. If you were to imagine the Milky Way as a vast, three-dimensional map of the universe, our solar system is positioned roughly two-thirds of the way out from the galactic center, approximately 27,000 light-years away from the heart of the galaxy. We occupy a region teeming with stars, planetary systems, and the interstellar material that makes up the fabric of the galaxy. Yet the Milky Way is far from a static structure. It is a living, breathing entity, constantly evolving and changing as stars are born, age, and die. The birth and death of stars in the galaxy leads to the formation of new cosmic structures, giving rise to nebula, star clusters, and the ongoing cycle of stellar evolution. As we consider our place in this grand galactic system, we are part of an immense and dynamic ecosystem of celestial bodies, each contributing to the rich tapestry of the universe. The spiral arms of the Milky Way are among the most striking features of this magnificent galaxy. These arms are formed through a complex interplay of gravity, motion, and the material that makes up the galaxy: gas, dust, and stars. To understand how they form, imagine the vast collection of material within the galaxy moving under the influence of gravitational forces. As these stars, gas, and dust swirl through space, they do not move uniformly. Instead, they collide and interact with one another, sometimes causing dense regions of material to clump together. This clustering of material is like the formation of traffic jams, where the density of matter increases due to gravitational attraction. Over time, this compression of material leads to the formation of spiral arms, which become clearly visible as the galaxy spins. These sweeping arms are not just beautiful features. They play a crucial role in the ongoing process of star formation. The gas and dust within these arms, compressed by gravity, become fertile ground for the birth of new stars. In this vast and continually evolving galaxy, the story of life's potential is just one chapter in an ongoing cosmic narrative, where the forces of nature continue to shape the universe in ways we are only beginning to understand. The Milky Way and the mysteries it holds offer us a glimpse into the past, present, and future of the cosmos, a reminder that our journey is part of something much larger than ourselves. Spiral arms are not merely beautiful patterns etched into the fabric of the night sky. They are the intricate tracings of cosmic processes that reveal the dynamic life of galaxies. These arms, visible across a vast number of galaxies, offer a glimpse into the rotational behavior of galaxies themselves, providing astronomers with vital clues about their ongoing evolution. As the galaxies spin, these spiral arms act as markers that track the gravitational interplay between stars, gas, and dark matter within them. But beyond their striking appearance, these arms serve as a cosmic canvas that tells the story of stellar birth, life, and death within the universe. At the heart of each spiral arm lies the light emitted by stars, which serve as time capsules. By studying this light, ranging from the faint glow of young stars to the fiery radiance of older ones, scientists can unravel the mysteries of a galaxy's composition, age, and the processes that shaped it. As stars are born in the dense clouds of gas and dust, their formation illuminates not just the present, but also provides an echo of the galaxy's distant past, telling of cosmic histories that stretch back billions of years. The spiral arms are thus not just picturesque structures, but vital signs of the forces that sustain galaxies. They are active birthplaces for stars, continuing to form new celestial bodies and often providing the conditions for even more spectacular phenomena, such as supernova explosions and the formation of planetary systems. In a sense, these arms function as a cosmic laboratory, where the interplay of gravity, magnetic fields, and radiation fosters the creation of new stars, allowing the galaxy to perpetuate its life cycle. Yet, these spiral arms are only a part of the story. At the very core of our galaxy, the Milky Way, lies one of the most enigmatic and powerful forces in the universe, a supermassive black hole known as Sagittarius A. This colossal entity, which holds a mass millions of times greater than our Sun, exerts an immense gravitational influence over the entire galaxy. Its presence has captivated astronomers and laypeople alike, as it holds the potential to answer some of the most profound questions about the nature of gravity, space-time, and the evolution of galaxies. The mystery of Sagittarius A lies in how such a massive black hole came into existence. Some theories propose that it formed from the merging of smaller black holes, while others suggest it grew over billions of years by drawing in vast quantities of gas and stars. Understanding the origins of this black hole not only sheds light on our galaxy's history, but also provides a broader framework for understanding the life cycle of galaxies themselves, how they grow, evolve, and eventually die. As fascinating as its origins are, the behavior of stars and gas near Sagittarius A is equally captivating. Astronomers have observed stars orbiting the black hole at astonishing speeds, revealing just how strong its gravitational pull truly is. These stars move in elliptical orbits, tracing paths that allow scientists to map the mass and size of the black hole with remarkable precision. But the exact mechanics of these orbits remain shrouded in mystery. How do these stars interact with the gravitational forces at play? What factors influence their movement? Understanding the dynamics of these stars not only informs us about the black hole, but also deepens our understanding of the forces governing the entire galaxy. The black hole's activity, or apparent lack thereof, adds another layer of intrigue. While it appears relatively calm compared to some other black holes scattered across the universe, it does exhibit periodic flares of energy. These bursts suggest that material is falling into the black hole, triggering events that release vast amounts of energy in the form of radiation. What causes these flares, and how does this process work on a microscopic level? These questions remain at the cutting edge of astronomical research, and each answer brings scientists closer to comprehending the mysteries of black holes. However, observing Sagittarius A is no easy task. It is hidden behind clouds of gas and dust, obscuring it from view in many wavelengths of light. To peer through this cosmic veil, astronomers rely on sophisticated tools such as radio waves and infrared telescopes. These technologies enable them to capture data and make observations that would otherwise be impossible. Every new discovery reveals another facet of this enigmatic region, further complicating our understanding of the black hole's nature and behavior. Sagittarius A is not just an isolated object, it is intimately tied to the Milky Way itself. The gravitational influence of this supermassive black hole extends far beyond its immediate vicinity, shaping the very structure and dynamics of the galaxy. The relationship between Sagittarius A and the rest of the Milky Way raises fascinating questions. How does its gravity influence star formation? What effect does it have on the galaxy's overall structure? How will this connection shape the future of our solar system and the fate of the galaxy itself? These are questions that continue to intrigue and inspire astronomers as they seek to unravel the mysteries of our cosmic home. But the story of our galaxy's formation is not confined to its center alone. The Milky Way's history stretches back over billions of years, beginning as pockets of gas and dust that collapsed under the force of gravity. Over time, this material came together to form the first stars, initiating a process of cosmic evolution that has shaped the galaxy into its current form. Imagine it like a snowball rolling down a hill. As more and more material accumulated, the process accelerated, leading to the formation of larger and more complex structures. As these first stars reached the end of their lives, they exploded in dramatic supernovae, enriching the surrounding gas with heavier elements. These elements, forged in the hearts of stars, became the building blocks for new generations of stars and planets. This cycle of birth, death, and rebirth continues to this day as new stars are constantly forming from the remnants of ancient ones. The ongoing creation of new stars within the Milky Way is a testament to the continuous and ever-evolving nature of the universe. Scientists believe that the Milky Way underwent several significant mergers with smaller galaxies during its early history. These galactic collisions had profound effects on the Milky Way's spiral structure and its gravitational dynamics, contributing to the shape we see today. The disk of the Milky Way, which is where most of its stars reside, acts as a stellar nursery, with new stars continually forming in regions where gas clouds condense under gravity. These new stars often interact with older ones, triggering bursts of new star formation and influencing the overall dynamics of the galaxy. The Milky Way, however, is far from a static object. It continues to evolve in the present day, slowly merging with nearby galaxies like the Large and Small Magellanic Clouds. These interactions create tidal forces that can trigger new star formation and even alter the orbits of stars and gas within the galaxy. These mergers serve as a reminder that the Milky Way is a dynamic, living entity, forever changing and adapting to the forces acting upon it. As astronomers delve deeper into the mysteries of the Milky Way, they turn to advanced tools like telescopes and computer simulations to study the galaxy's dark matter halo. This invisible substance, which makes up a significant portion of the galaxy's mass, exerts a powerful gravitational influence, helping to bind the stars and gas together. Understanding the role of dark matter in the galaxy's formation and evolution is one of the most pressing challenges in modern astronomy. The story of the Milky Way is one of cosmic evolution on a grand scale, a story of gas, dust, and stars coming together to form the majestic spiral galaxy we call home. From its humble beginnings to its current form, the Milky Way is a living testament to the forces that shape galaxies and the universe itself. It is a reminder of the intricate interconnectedness of cosmic processes and the awe-inspiring scale of the universe in which we reside. One of the most intriguing regions within the Milky Way is the Orion Arm, a spiral arm that serves as a laboratory for astronomers to study star formation and the complex dynamics of our galaxy. This arm, which is approximately 1,000 light-years wide, is home to numerous stars, nebulae, and other celestial objects, all of which provide valuable insights into the structure and composition of the galaxy. The Orion Nebula, a well-known star-forming region, is just one example of the incredible processes at work within the Orion Arm. Here, vast clouds of gas and dust are compressed by gravity, igniting nuclear fusion and giving birth to new stars. By studying the Orion Arm, astronomers are able to model the processes that drive star formation, shedding light on how stars are born not just in our own galaxy, but in galaxies across the universe. This knowledge is crucial for understanding the larger cosmic picture and the intricate mechanisms that govern the formation and evolution of galaxies. In essence, the Orion Arm offers a window into the heart of the Milky Way, allowing us to peer into the ongoing process of stellar birth and death and to explore the fundamental forces that shape the cosmos. Through the study of this remarkable region, we can begin to appreciate our place in the universe and the profound connections that link us to the stars above. The Orion Arm, a key region in our Milky Way galaxy, is home to some of the most iconic and recognizable stars, such as Betelgeuse and Rigel. These celestial giants do more than just light up our night sky. They serve as essential markers for mapping the distances and motions of stars within our galaxy. Their importance extends far beyond their visual appeal, as they help astronomers track the dynamic behavior of stellar motion. Through comparative studies of stars like Betelgeuse and Rigel, researchers are able to peel back the layers of cosmic mysteries, revealing insights into the intricate dance of stars within our galaxy. The Orion Arm, where our solar system resides, offers a unique vantage point for understanding how different parts of the galaxy interact with one another. By studying these stars and their relationships, scientists can uncover the hidden forces that shape stellar evolution and their broader roles in the structure of the universe. This region provides a fascinating glimpse into the vast cosmic web, the large-scale structure of the universe itself. The Orion Arm, far from being an isolated entity, is one part of a sprawling network of stellar arms and regions, all interconnected in ways that influence everything from galaxy formation to the distribution of mass across the cosmos. When astronomers delve into the study of the Orion Arm, they are not just learning about a specific section of the Milky Way. Instead, they are piecing together a grander cosmic puzzle, one that helps us understand the distribution of mass and the gravitational forces at play throughout the galaxy. By examining the Orion Arm, scientists gain valuable insights into how these forces influence the movement of stars, galaxies, and other cosmic objects. Each new discovery helps to deepen our understanding of the universe's history and structure, teaching us not only about our local cosmic neighborhood, but also about the fundamental forces that govern the cosmos. Moving from stars to the remnants of their death, neutron stars are among the most fascinating and enigmatic objects in the universe. These dense, compact remnants of massive stars arise after a star has gone through a supernova explosion, the cataclysmic final act in the life cycle of a star. Imagine, if you will, a star far larger than our Sun. As this star consumes its nuclear fuel, it loses the ability to counterbalance the immense force of gravity pulling inward. When this balance tips, the core of the star collapses under its own weight, causing protons and electrons to merge into neutrons. This process forms a neutron star, a mind-bogglingly dense object where mass greater than that of our Sun is packed into a sphere no larger than a city. The result is a neutron star that is so dense that a mere spoonful of its material would weigh as much as an entire mountain. Along with its incredible density, the collapse of the star also triggers a dramatic supernova explosion that scatters the outer layers of the star into space. This explosion not only marks the death of a star, but also enriches the interstellar medium with elements that could later give rise to new stars and planets. The neutron star itself remains as a rapidly spinning remnant, often possessing a powerful magnetic field. This magnetic field can generate beams of radiation, which, if they happen to be directed toward Earth, are detected as regular pulses. These pulsations, which are characteristic of neutron stars, are the subject of intense study. When these stars emit beams of radiation, they sweep across space like the beam of a lighthouse, producing regular pulses of electromagnetic waves. These pulses, which are often in the form of radio waves or other types of radiation, allow astronomers to gather crucial data about the neutron star and its surroundings. If the beam of radiation points toward Earth, we can observe these pulses as rhythmic flashes, a cosmic rhythm that is both captivating and informative. In a way, neutron stars act as cosmic timekeepers. Their regular pulses are not only mesmerizing, but also serve as precise clocks that rival atomic timepieces in their accuracy. This regularity is particularly valuable in the study of the fundamental laws of physics. For example, any slight variations in the timing of these pulses can reveal the presence of gravitational forces acting on the neutron star, suggesting the influence of nearby companion stars or other celestial bodies. By analyzing these pulse patterns, astronomers can unravel the dynamics of binary star systems, where two stars orbit one another. Pulsars, a particular type of neutron star, offer even deeper insights into the fabric of the universe. These highly magnetized, rapidly rotating neutron stars emit beams of electromagnetic radiation, much like the beam of a lighthouse, but at regular intervals. The extreme conditions around these stars, such as their incredibly strong gravitational fields and their rapid spin rates, make them natural laboratories for testing the laws of physics. Pulsars, with their dense cores and powerful magnetic fields, provide a unique environment for astronomers to explore some of the most fundamental aspects of the universe, including gravity, the strong nuclear force, and the nature of space-time itself. One of the most fascinating aspects of pulsars is their role in our understanding of binary systems. When pulsars are part of a binary system where two stars orbit each other, they can be used to study the intricate interactions between the two stars. The timing of the pulses emitted by the pulsar can reveal subtle details about the gravitational forces at play, such as the presence of a companion star or even the motion of the pulsar through space. These studies help scientists understand how stars and other celestial bodies influence one another in ways that are difficult to observe directly. Moreover, the regularity of pulsar pulses makes them invaluable tools for studying the nature of space-time itself. In particular, millisecond pulsars that spin at incredibly fast rates, have been used to probe the effects of gravity and other fundamental forces under extreme conditions. By studying the spin rates of these pulsars, scientists can gain a deeper understanding of how matter behaves under intense gravitational fields. These investigations contribute to our broader knowledge of fundamental physics, shedding light on the forces that govern the universe and the laws that underlie its structure. In many ways, pulsars serve as cosmic laboratories, offering a window into some of the most extreme and mysterious phenomena in the universe. Through the study of these incredible objects, astronomers continue to push the boundaries of our understanding, revealing the inner workings of the universe in ways that were once thought to be beyond our reach. Pulsars, neutron stars, and the larger structures of the cosmos are all part of a vast and interconnected network, each piece contributing to the grand story of the universe's evolution and the forces that shape it. By studying these celestial objects, we continue to unlock the secrets of the cosmos, gaining insights not only into the history of stars, but also into the fundamental nature of the universe itself. Astronomers have long relied on the use of pulses as cosmic reference points, helping to map the vast expanse of the universe. These pulses, which originate from various celestial bodies, are not just fleeting signals. They are key to unlocking the secrets of the cosmos. By studying the signals from pulsars, scientists gain insights into the very structure and scale of the universe. The data gathered from these pulsations can provide a detailed understanding of cosmic distances, enabling researchers to draw more accurate maps of the universe's large-scale architecture. The process of studying these pulsar signals doesn't stop at just measuring their arrival times. By analyzing how these signals disperse as they travel across the vastness of space, scientists are able to detect the subtle influences of interstellar matter. This phenomenon, known as dispersion, can offer clues about the composition and density of the material scattered throughout the galaxy. As the signals pass through different regions of space, the delay and distortion of the pulses are directly affected by the intervening medium, allowing astronomers to infer the properties of the gas, dust, and other elements that populate our galaxy. But pulsars are not just ordinary remnants of dead stars. They are invaluable tools that help unravel some of the most perplexing mysteries of the universe. Pulsars, along with their more exotic cousins, the magnetars, serve as cosmic laboratories where the laws of physics are pushed to their very limits. They offer an unprecedented opportunity to explore the behavior of matter under extreme conditions and gain a deeper understanding of the forces that govern the cosmos. Magnetars, in particular, are a type of neutron star that is especially fascinating due to their incredibly strong magnetic fields, which are among the most powerful in the entire universe. To comprehend the sheer scale of a magnetar's magnetic strength, imagine a neutron star, which is the collapsed core of a star that has exploded in a supernova. A typical neutron star is already extraordinarily dense, packing a mass greater than that of the Sun into a sphere only a few miles across. Now, picture that this already dense object has a magnetic field so powerful that it can be 1,000 trillion times stronger than Earth's own magnetic field. To put that in perspective, merely being near a magnetar could disrupt electronics or even distort the physical structure of nearby objects. These immense magnetic forces can release bursts of energy so intense that they temporarily outshine entire galaxies. When a magnetar undergoes one of these explosive events, it emits vast amounts of energy in the form of gamma rays and X-rays, which makes it detectable from across great distances. These outbursts are short-lived, but they are extremely powerful, offering a glimpse into the behavior of matter and energy under the most extreme conditions known to science. The magnetic field of a magnetar is not just a curiosity, it is a window into the fundamental laws of physics, testing our understanding of how matter behaves in environments with such intense gravitational and magnetic forces. But the magnetar's magnetic field is just one of the extreme features that make these objects so intriguing. The surface temperature of a magnetar can reach unimaginable heights, and the high-energy radiation it emits is yet another layer of complexity. Together, these characteristics make magnetars a unique subject of study in astrophysics, as they challenge our current understanding of the laws that govern the universe. Their extreme magnetism, combined with their energetic outbursts, serves as a natural laboratory for studying the behavior of matter, radiations, and gravity under conditions far beyond what we can replicate on Earth. Neutron stars themselves are among the most extraordinary objects in the universe. They represent the final, often mind-boggling stages of stellar evolution, and they offer profound insights into the nature of matter. When a massive star exhausts its nuclear fuel, it undergoes a dramatic supernova explosion, leaving behind a dense core. This core collapses under the force of gravity, compressing its mass into a space so small that a single teaspoon of neutron star material would weigh more than all of humanity combined. The density of a neutron star is so extreme that the very concept of atomic behavior dissolves. In place of atoms, there exists a tightly packed sea of neutrons, all bound together by immense gravitational forces. This extreme compression is the result of the merging of protons and electrons to form neutrons. As these neutrons are tightly packed, the matter inside a neutron star becomes a state of matter unlike anything we experience on Earth. The forces involved in such a dense, compact object push the limits of our understanding of physics. In such an environment, the strong nuclear force, which is typically responsible for holding atomic nuclei together, is stretched to its maximum limits. Meanwhile, the gravitational forces at play are so powerful that they alter the very fabric of space and time itself. At the heart of a neutron star lies a mystery. What exactly happens at its core? The densities and pressures at the center of a neutron star exceed anything we can replicate on Earth, and this raises intriguing questions about the possible existence of new states of matter. Could quark-gluon plasma, a state of matter where quarks are no longer bound in protons and neutrons, exist there? This state of matter, theorized to exist just moments after the Big Bang, could hold the key to understanding how the universe evolved in its earliest moments. In addition to their extreme density, neutron stars also exhibit astonishing rotational behavior. Some neutron stars spin at incredible speeds, completing several rotations per second. This rapid spinning generates intense magnetic fields, which can produce beams of radio waves that sweep across space, creating the phenomenon known as pulsars. The rotation of a neutron star challenges our understanding of physics in profound ways, inviting scientists to rethink concepts such as energy, momentum, and angular momentum. The extreme rotational velocities of neutron stars also offer insight into the fundamental forces at work in the universe, providing a unique opportunity to test current physical theories, including the theories of relativity and quantum mechanics. Neutron stars also serve as natural laboratories for studying the extreme conditions found in binary star systems. In such systems, a neutron star can draw material from its companion star, forming an accretion disk around the neutron star. This process can lead to the release of enormous amounts of radiation, including powerful bursts of X-rays. In some cases, these systems produce the phenomenon known as X-ray binaries, where the interaction between the neutron star and its companion star results in some of the brightest and most energetic objects in the universe. In essence, neutron stars are more than just remnants of dead stars. They are a window into the very heart of the universe, offering a glimpse into the fundamental forces and particles that govern everything from the smallest particles to the largest structures in the cosmos. Each discovery about neutron stars, whether it be about their magnetic fields, their extreme densities, or their rotational behaviors, brings us one step closer to understanding the deepest mysteries of the universe. As scientists continue to study these extraordinary objects, they continue to push the boundaries of what we know about the cosmos and the laws of physics themselves. Neutron stars are not only captivating stellar remnants, but they also serve as crucial players in some of the most energetic and cataclysmic events the universe has to offer. These events include gamma ray bursts, which rank among the universe's most powerful and violent explosions. When two neutron stars collide, they do not merely merge, they unleash a series of complex processes that shape the very fabric of the cosmos. These cosmic collisions produce heavier elements like gold and platinum, elements essential for the formation of planets and life as we know it. Alongside this, the collision emits intense beams of gamma radiation, the most powerful form of electromagnetic energy. These bursts of gamma rays travel vast distances across the universe, giving us a glimpse into the energetic forces at work far beyond our own galaxy. Yet, the drama of these collisions doesn't end with the emission of radiation. They also generate gravitational waves, ripples in the very fabric of space-time. These waves are the cosmic echoes of a violent event that reverberates through the universe, carrying with them valuable information about the nature of the collision. It is through the detection of these gravitational waves that astronomers have been able to peer deeper into the heart of these colossal events. In fact, the very first detection of such waves in 2015 was a monumental achievement in the field of physics, as it confirmed Einstein's century-old predictions about the nature of space-time itself. Gravitational waves provide us with an entirely new way of observing the universe. They are caused by the acceleration of massive objects like black holes or neutron stars, which disturb the space around them. To understand this better, imagine dropping a stone into a still pond. The surface of the water creates waves that ripple outward from the point of impact. Similarly, when two massive objects move through space, their motion creates disturbances in the space-time fabric. These ripples spread outward at the speed of light, carrying with them vital information about the object's properties and the nature of their interactions. The first confirmation of gravitational waves occurred after the collision of two black holes, over 1 billion light-years away. As these two massive black holes spiraled toward one another, they released an immense amount of energy. This energy traveled across the cosmos in the form of gravitational waves. When these waves reached Earth, they caused minuscule fluctuations in the lengths of the tunnels at the Laser Interferometer Gravitational Wave Observatory, LIGO, located in the United States. These fluctuations were so small, on the order of 1,000th of the diameter of a proton, that detecting them required extraordinary precision. Yet, despite the minuscule nature of the waves, they carried with them vital information about the properties of the black holes involved, such as their masses, spins, and the dynamics of their final moments before merging. This discovery not only confirmed the existence of gravitational waves, but also provided the first direct observation of a black hole merger. Through gravitational waves, scientists can now listen to the universe in a way that was previously unimaginable. These waves provide a unique soundtrack to some of the most violent and energetic events in the cosmos. Each gravitational wave event tells a story, an unfolding narrative of the merging of massive objects, the release of energy, and the subsequent ripples that spread throughout space-time. By studying these waves, researchers can gain insights into phenomena that were once hidden from view, such as the precise nature of black hole collisions or the intricate details of neutron star mergers. In addition to providing new information about the universe's most extreme events, gravitational waves have opened a new frontier for scientific exploration. As astronomers continue to detect and analyze these waves, they uncover more about the lives of massive cosmic objects, the nature of gravity, and the fundamental workings of space-time itself. Each detection adds another layer to our understanding of the universe, moving us ever closer to understanding the forces that shape the cosmos. The study of neutron stars, black holes, and gravitational waves is reshaping our understanding of the universe. These phenomena are not just abstract concepts, they are integral to the ongoing evolution of galaxies, the recycling of cosmic material, and the formation of new stars and planetary systems. Through their life cycles and interactions, these stellar remnants contribute to the very creation of elements like gold and platinum, which form the building blocks for the planets we inhabit. As we continue to study these objects and the waves they generate, we gain a deeper appreciation for the intricate, interconnected nature of the cosmos. Space-time, once thought of as a static backdrop to cosmic events, is now understood to be a dynamic, ever-changing arena. When massive objects such as neutron stars or black holes collide, they create ripples that propagate outward, carrying vital information about the forces at play. By detecting and analyzing these gravitational waves, scientists are beginning to unlock the secrets of the universe's most energetic processes, expanding our view of the cosmos in ways that were once thought impossible. In many ways, gravitational waves are the universe's way of revealing its most dramatic stories. As these waves travel through space, they carry with them the signature of the events that created them. Be it the collision of two black holes, the merging of neutron stars, or other equally violent processes. Each wave contains a wealth of information, offering us a new lens through which to observe and understand the cosmic dance of the universe's most massive objects. Through this groundbreaking discovery, we are on the verge of a new era in astronomy, one that promises to deepen our knowledge of the universe and the fundamental laws that govern it. These discoveries also have profound implications for the ongoing study of gravity. Traditionally, gravity has been understood through the lens of Newton's laws and Einstein's theory of general relativity. But gravitational waves allow us to test these theories in ways that were previously unimaginable, pushing the boundaries of our understanding of the force that governs the motion of all objects in the universe. By observing the way these waves interact with space-time, scientists are able to refine their models of gravity, uncovering new insights into its nature. Ultimately, the study of neutron stars, black holes, and gravitational waves is about more than just observing distant cosmic events. It's about understanding the underlying forces that shape the universe itself. These discoveries provide a glimpse into the deep, interconnected web of forces that govern the evolution of galaxies, stars, and planetary systems. As we continue to explore these phenomena, we come closer to answering some of the most profound questions about the universe, its origins, and its ultimate fate. Through the study of gravitational waves and the objects that create them, we are learning more than ever before about the vast, complex, and dynamic universe in which we live. Gravitational wave astronomy is rapidly transforming the landscape of modern astrophysics, offering a new window into the most dramatic and energetic processes occurring across the universe. With every detection, scientists are uncovering a vast array of new insights that were once beyond the reach of traditional observation methods. This revolutionary field, spurred on by breakthroughs in technology and innovative experimental techniques, is not only confirming Einstein's theoretical predictions, but also unveiling phenomena that challenge and expand our understanding of the very fabric of space-time itself. Gravitational waves, ripples in the fabric of spacetime, are produced by extremely massive and accelerating objects. These waves are generated by events such as the collision of black holes, the merging of neutron stars, or the catastrophic death throes of massive stellar remnants. Unlike light or other forms of electromagnetic radiation, which can be blocked, absorbed, or scattered by intervening matter, gravitational waves travel unimpeded through the cosmos. This makes them a unique and powerful tool for observing the universe. They carry with them information about their sources, often from billions of light years away, providing an unparalleled view into some of the most energetic and elusive events in the universe. Through the lens of gravitational waves, space-time is revealed not as a static backdrop to the cosmos, but as a dynamic, malleable entity that is constantly being shaped by the cosmic processes that govern the universe. The detection of these waves has confirmed many of the profound predictions made by Einstein in his theory of general relativity. For example, these waves vividly demonstrate how extreme gravitational interactions can warp and distort the surrounding space-time, causing phenomena such as the bending of light and the slowing of time in regions with intense gravitational fields. This not only reshapes our understanding of gravitational physics, but also raises tantalizing questions about the nature of reality itself. Each wave detected offers a snapshot of a dramatic cosmic event. By analyzing these ripples, scientists are able to probe the properties of the objects that created them. how massive they were, how fast they were moving, and the conditions under which they existed. These insights offer new opportunities to understand the most extreme environments in the universe, including black hole mergers and neutron star collisions, both of which can't be observed using traditional telescopes. The signals captured by gravitational wave detectors are often invisible to light-based instruments, yet they can contain rich information about the fundamental nature of matter and energy in these regions. As our technology improves, we are entering an exciting new era of multi-messenger astronomy, where, for the first time, we are able to study cosmic events through multiple forms of radiation simultaneously. This approach allows us to view the same phenomenon through different lenses: light waves, gravitational waves, and other signals such as neutrinos. By combining these various observations, we gain a deeper understanding of how stars evolve, how galaxies form, and how the fundamental forces of nature operate across vast scales of time and space. This fusion of different observational methods opens new pathways to understanding the universe in ways that were previously unimaginable. The study of gravitational waves does more than simply broaden our knowledge of specific cosmic events. It fundamentally challenges our understanding of physics itself. As we refine our detection capabilities, we are paving the way for discoveries that could reshape our concepts of gravity, mass, and the universe's very origins. With every new detection, we move closer to answering profound questions about the structure of the universe and the mysteries that lie beyond our current comprehension. One of the most compelling aspects of gravitational wave astronomy is its ability to reveal the hidden world of black holes, particularly those involved in mergers. By studying these cataclysmic events, we can learn more about the distribution of black holes throughout the universe, offering clues about their formation and evolution. These observations may also provide a deeper understanding of the extreme conditions near black holes, testing the limits of Einstein's theory of general relativity and shedding light on how gravity behaves in the most intense environments. Moreover, the study of black hole mergers is poised to open up new questions about the very nature of space-time itself, questions that have long puzzled physicists. Another area of great promise lies in the observation of neutron star mergers. These violent collisions not only generate gravitational waves, but also produce electromagnetic signals, such as gamma-ray bursts, that can be detected by traditional telescopes. By studying these events across both gravitational and electromagnetic spectra, scientists can gain new insights into the process of nuclear synthesis, the creation of heavy elements such as gold and platinum in the universe. These elements, which are critical to the composition of planets, stars, and life itself, were once thought to be beyond our reach. However, neutron star mergers could hold the key to answering the age-old question of how these heavy elements are forged in the heart of the cosmos. Perhaps the most ambitious and exciting frontier in gravitational wave astronomy lies in its potential to shed light on the very early universe. Theories suggest that gravitational waves could provide a glimpse into the conditions that existed just minutes after the Big Bang, a period of rapid expansion known as inflation. If we can trace these primordial waves, scientists may be able to gather evidence about the inflationary phase that shaped the universe's earliest moments. Such discoveries would provide a direct probe into the conditions that gave rise to the universe we see today, offering an unprecedented window into the origins of everything. As the field of gravitational wave astronomy continues to evolve, we can expect to encounter even more exotic phenomena that challenge our current understanding of physics. For example, the next generation of gravitational wave detectors may uncover the existence of new types of compact objects that we haven't yet imagined, such as hidden black holes or other strange entities that lie outside the scope of our current models. These discoveries could lead to new theories of physics that redefine what we know about the fundamental forces of nature. Gravitational wave astronomy is not just a new way of observing the universe. It is a revolution in how we think about the cosmos itself. With each new discovery, we are rewriting the history of the universe, peering deeper into its most mysterious and enigmatic corners. And as our ability to detect and analyze gravitational waves improves, We are poised to make discoveries that will fundamentally alter our understanding of the universe, its origins, and its ultimate fate. Moreover, imagine the revolutionary potential of utilizing gravitational waves to study the intricate dynamics of massive galaxies and their complex interactions. By observing these waves emanating from the supermassive black holes nestled in the centers of galaxies, we could unlock secrets about galaxy formation and behavior across the vast expanse of cosmic time. Gravitational wave astronomy stands on the precipice of an exciting frontier, offering unprecedented insight into the workings of the universe. The future promises a profound expansion of our understanding, not only about the cosmos itself, but also about the fundamental forces that govern it. With each new discovery, we inch closer to uncovering truths that could fundamentally redefine the very fabric of reality. In this context, we also find ourselves drawn to the enigmatic existence of rogue planets, celestial bodies that drift through space, unmoored from the gravitational embrace of any star. These wandering planets, unlike the typical exoplanets that orbit stars, defy the conventional patterns of the cosmos. They are the cosmic nomads, free roaming in the vast expanse of the galaxy, journeying across the unknown voids of space. They have either formed in isolation or been violently ejected from their original star systems due to gravitational disruptions. Their existence challenges everything we thought we knew about planetary behavior and the intricate dance of celestial bodies. While traditional exoplanets are inextricably bound to their parent stars, relying on the star's warmth and light for sustenance, rogue planets live in stark contrast. They do not trace predictable orbits around a central sun. Instead, they meander through the dark, unilluminated by the familiar glow of a distant star. This absence of a stellar relationship removes them from the dance of the solar system, leaving them to drift alone in the emptiness of space. Their existence is one of mystery and defiance as they continue their lonely journey across the galaxy. The origins of rogue planets are as varied as their paths. Some are born in the cold, distant outskirts of a star system, where the gravitational forces within the system can send them hurtling away into the void. Others are the tragic remnants of catastrophic collisions or stellar disruptions flung out by the violent forces at play when celestial bodies interact. These rogue wanderers may still retain some familiar characteristics, atmospheres, geological features, or even the potential for life. However, the absence of sunlight drastically alters the conditions that we are used to when studying life-sustaining environments. Still, they remain fascinating objects of study, offering astronomers unique challenges and opportunities. Detecting rogue planets is no simple feat. Unlike their sunbound cousins, they do not reflect the light of a nearby star, making them nearly invisible in the vast stretches of space. Instead, astronomers rely on specialized techniques, such as studying subtle gravitational effects or the faint glimmer of heat that these planets may emit. This requires a shift in our understanding of how we perceive and detect celestial bodies. Rogue planets represent a new and exciting chapter in our exploration of the universe, pushing the boundaries of planetary science. Rogue planets, as wandering worlds untethered to any star, may originate from a variety of fascinating scenarios. One popular theory suggests that rogue planets form in much the same way as traditional exoplanets, within a protoplanetary disk around a young star. However, in these scenarios, gravitational interactions with other celestial bodies can disrupt this process. If two planets within a star system come too close, one might be ejected by the other's gravitational force, flung away from the safety of the star and into the great unknown. Another theory points to the crowded, dynamic environments of star clusters, where the gravitational forces between stars and planets are constantly at play. In these dense regions, a planet might be ejected during a close encounter with a larger body or another planet, creating another pathway for the formation of rogue planets. Some scientists also propose that rogue planets might form in the cold, dark regions of space, far from any stars. In these isolated pockets, gas and dust can coalesce into planets, independent of any stellar influence. These isolated worlds would then embark on a journey through space, unanchored by any sun, creating a hidden population of planets that we are only beginning to understand. As these rogue planets drift through the cosmos, they add to the complexity of the universe's planetary population, challenging our preconceived notions about how planets form and survive. They exist in a state of perpetual motion, constantly shifting through the galaxy without the gravitational anchor of a star. This creates a rich tapestry of celestial bodies, some securely tethered to their suns, and others adrift in the great expanse of space. The study of these rogue planets enriches our understanding of planetary evolution and the diversity of the universe's structures. The prospect of life on rogue planets presents yet another intriguing question. Unlike planets that reside within a solar system, these solitary worlds lack the warmth and light of a nearby star. At first glance, their cold, dark existence seems to make them inhospitable to life. However, under the right conditions, life may still find a way to thrive. One of the most significant factors to consider is the internal heat that these planets might retain. During their formation, rogue planets could have accumulated geothermal energy, which could create pockets of warmth beneath their surfaces. These subsurface regions could harbor oceans or other liquid environments, much like those suspected to exist beneath the icy crusts of moons such as Europa or Enceladus. In such conditions, microbial life or other simple organisms could potentially survive, relying on the geothermal energy for warmth, much like the organisms found near Earth's deep-sea hydrothermal vents. Moreover, life on these planets could thrive without relying on sunlight. On Earth, certain organisms have adapted to live in complete darkness, deriving energy not from the sun but from chemical reactions, a process known as chemosynthesis. In theory, if a rogue planet has the right chemical ingredients, it could foster life in a similar way, utilizing its own mineral resources to sustain biological processes. Additionally, a thick atmosphere could play a key role in supporting life on rogue planets. If a rogue planet has a dense atmosphere, it could help retain heat, maintaining conditions that could allow liquid water to exist on the surface. Water is often cited as a crucial element for the development of life, so the presence of liquid water combined with internal heating and chemical energy could offer the right conditions for life to flourish in ways we have yet to fully comprehend. While the lack of sunlight on rogue planets presents significant challenges, the potential for life remains a tantalizing possibility. These mysterious worlds, with their geothermal energy, chemical potential, and atmospheric conditions, may harbor life forms that are vastly different from anything we recognize. In the end, rogue planets are a testament to the resilience of life, its ability to adapt and thrive in even the most extreme and unexpected environments of the universe. As we continue to study these wandering worlds, we may uncover new forms of life and new insights into the nature of existence itself. Detecting these rogue planets is no small task. Since they do not reflect the light of a nearby star, astronomers must rely on novel methods to identify them. This often involves studying the subtle gravitational effects these planets exert on nearby objects or detecting the faint heat they emit. The search for rogue planets is a challenge, but it is also a journey that promises to deepen our understanding of the universe and expand the boundaries of what we consider possible in the cosmos. However, astronomers have developed a range of innovative methods to detect and study the enigmatic nature of rogue planets, celestial bodies that drift through space without a star to call their own. One of the primary techniques involves observing the gravitational influence these rogue planets have on nearby objects. When a rogue planet passes close enough to another celestial body, it can subtly alter that body's trajectory, nudging it slightly due to the planet's gravitational pull. By monitoring these minute changes in the object's path, astronomers can infer the presence of the rogue planet, even though the planet itself may remain hidden in the vastness of space. Another powerful method relies on a phenomenon known as gravitational microlensing. When a rogue planet aligns with a distant background star, the gravitational field of the rogue planet bends and magnifies the light from that star. This effect creates a temporary brightening or lens flare that is visible from Earth. Through this phenomenon, astronomers can detect objects that would otherwise be invisible to our naked eye. By carefully analyzing the light curves, how the light intensity fluctuates during the event, researchers can extract valuable information about the rogue planet's mass, its distance from Earth, and other physical properties. In addition to gravitational methods, astronomers have turned to infrared detectors to help spot rogue planets. These objects, especially if they are relatively young and still cooling from their formation, emit infrared radiation, heat that human eyes cannot detect. These detectors are specifically tuned to capture infrared wavelengths, revealing the planet's presence through its thermal emissions. This technique has been pivotal in unveiling rogue planets that are too faint to be seen in visible light, contributing to the growing body of knowledge about these solitary wanderers of the cosmos. Through the use of these techniques, astronomers are gradually piecing together the elusive lives of rogue planets, constructing a more complete picture of the diverse array of worlds that exist beyond the reaches of known stars. This expanding knowledge not only fuels our curiosity about these isolated planets, but also provides deeper insight into planetary formation, star system dynamics, and the broader workings of our universe. Rogue planets, those solitary travelers adrift through the cosmos without the gravitational anchor of a parent star, challenge our traditional understanding of planetary systems. They reveal that the universe is not just composed of planets revolving around stable stars. It is also a dynamic, ever-changing place where worlds can be ejected from their original systems due to gravitational interactions. Imagine, if you will, a planet once part of a vibrant solar system, a world that was once nestled within the gravitational embrace of its parent star, now dislodged and cast adrift, sailing alone through the endless void of space. This image forces us to rethink the very nature of planetary systems, encouraging us to explore how such rogue worlds could have formed. Traditionally, we associate planets with stable orbits around stars, but the existence of rogue planets suggests there might be alternative scenarios at play. These planets may form in isolation, potentially emerging from dense gas clouds only to be expelled from their birthplaces later in their existence. This hypothesis invites scientists to explore the possibility that some planets might never have had a star to begin with, existing instead in a state of independence. These planets could potentially host unique environments, perhaps even supporting forms of life that are radically different from anything we associate with star-bound planets. Furthermore, the presence of rogue planets could also lead to a reshaping of our theories on planetary formation and evolution. By studying these lone wanderers, astronomers can learn more about the intricate processes that govern the birth and growth of planets. Understanding the mechanics behind how a planet might be ejected from its parent system provides crucial clues about the forces at work in the cosmos. It also raises important questions about the frequency of collisions or interactions between rogue planets and other celestial bodies. Such encounters could create new planetary systems or even influence the fate of existing ones, further enriching our understanding of the universe's complexity. Rogue planets, in their isolation, serve as a reminder of the vast number of mysteries that still remain hidden within the cosmos. Their very existence opens up new lines of inquiry into how they might interact with the broader cosmic environment. For instance, these planets could influence gravitational dynamics or even trigger the migration of other celestial objects, shifting the balance of matter and energy in their immediate vicinity. As we continue to refine our observational tools and methodologies, our ability to detect and study these rogue planets grows, bringing us closer to understanding their role in the universe. Through these studies, we begin to realize that planetary systems are not static entities. Rather, they are ever-evolving, filled with the potential for chaos, complexity, and change. In parallel to the study of rogue planets, astronomers also delve into the nature of cosmic voids, vast, empty regions of space that stretch between the filaments and clusters of galaxies. These voids form a strikingly fascinating structural component of the universe, helping to shape the overall arrangement of cosmic matter. Picture, if you will, the universe as a vast web, where the strands represent clusters of galaxies that are woven together into intricate patterns resembling bubbles in a frothy drink. The empty spaces between these strands, the voids, are immense expanses where matter is relatively scarce. These voids can stretch across billions of light years, distances so vast that they almost defy comprehension. While these regions contain far fewer galaxies and much less dark matter than the dense areas of the universe, they are not entirely devoid of structure. Occasionally, a few isolated galaxies or small clusters can manage to thrive in the emptiness, adding a unique layer to our understanding of cosmic evolution. Structurally, cosmic voids are integral to the formation and development of the universe. They provide critical insight into how galaxies have formed and evolved over cosmic time. By studying these voids, scientists are better equipped to understand the gravitational forces that shape the universe and how matter is distributed across its grand scale. Moreover, voids play an important role in the ongoing expansion of the universe. As the cosmos continues to grow, these empty regions expand as well, subtly influencing nearby galaxies and structures. This expansion is a driving force in the dynamic processes that shape the universe's ongoing evolution, making voids essential to our understanding of cosmic history. Interestingly, cosmic voids also challenge our traditional views of galaxy formation and clustering. These regions are unexpectedly large and relatively empty, presenting a stark contrast to the dense, bustling galaxy clusters that fill the more active regions of the universe. To visualize this, imagine a sponge filled with water, where the water represents galaxies and the air pockets correspond to voids. The presence of voids with their sparse distribution of matter suggests that not all regions of the universe have gone through the same processes of collapse and growth that typically lead to the formation of galaxies. Traditional models of galaxy formation emphasize the role of gravity in drawing matter together to create stars and galaxies. However, in the vast emptiness of these voids, the lack of matter means fewer galaxies can form, and those that do tend to be more isolated and unique. Moreover, cosmic voids exert a powerful influence on the galaxies that reside near their edges. Galaxies on the periphery of these voids experience different gravitational effects compared to those embedded in denser clusters. This variance can lead to peculiar motions in galaxies, as well as variations in their composition, adding yet another layer of complexity to our understanding of how environmental factors affect the evolution of galaxies. Recent studies have also uncovered a fascinating potential link between cosmic voids and dark energy, the mysterious force believed to be driving the accelerated expansion of the universe. This connection adds a new level of complexity to the study of voids and their role in the cosmos. As astronomers continue to explore the nature of these vast, empty spaces, they may uncover groundbreaking insights into the underlying forces that have shaped the universe since its inception. Astronomers employ a range of sophisticated techniques to study these cosmic voids, and mapping these vast emptinesses has become an essential part of understanding the structure of the universe. Large-scale surveys of the night sky, which systematically catalog the positions and distribution of galaxies, provide the foundational data for studying voids. One key method is redshift surveys, where astronomers measure the redshift of light from distant galaxies. This redshift indicates how fast the galaxies are moving away from us, and from this data, scientists can calculate their distance. By mapping the three-dimensional distribution of galaxies, astronomers can visualize how voids fit into the larger cosmic structure. Another critical tool for studying cosmic voids is the analysis of the cosmic microwave background radiation, the afterglow of the Big Bang. Fluctuations in this ancient light offer a snapshot of the universe in its earliest stages, revealing the distribution of matter, both visible and dark. By studying these fluctuations, astronomers can infer the structure of the universe on the largest scales, including the distribution of cosmic voids. This insight provides a deeper understanding of the forces that have shaped the cosmos over billions of years. Through these techniques and continued research, astronomers are uncovering the profound significance of cosmic voids in shaping the universe, challenging our understanding of the cosmos, and offering new perspectives on the mysteries that continue to unfold across the vast expanse of space. Cosmic voids, some of the most enigmatic and vast regions in the universe, continue to intrigue astronomers and scientists. These voids are enormous, underdense expanses where galaxies are sparse or completely absent. Unlike the dense regions filled with rich clusters of galaxies, cosmic voids offer a stark contrast, both in terms of physical structure and dynamics. While much of the universe is teeming with the gravitational pull and interactions between galaxies, voids are surprisingly tranquil, shaped by forces on a grander scale, such as the expansion of the universe itself. Astronomers have long sought to better understand these voids, as they hold key insights into the very nature of the universe's evolution. One of the most powerful tools in this endeavor is the use of computer simulations. By modeling the large-scale structure of the universe, these simulations account for various factors such as dark matter and gravitational influences. These forces are critical in shaping how galaxies and voids form and evolve over time. The ability to compare real observational data with these simulations has enabled researchers to refine their understanding of cosmic voids, gaining valuable insights into their origins and the role they play in the broader cosmic story. Through these simulations, scientists can explore the intricate dynamics of cosmic voids. These regions are characterized by a profound scarcity of galaxies, and their empty expanses are shaped primarily by the universe's expansion. In these voids, the gravitational forces that typically draw galaxies together are much weaker. The result is a more isolated existence for the galaxies within them. They can drift apart from one another as the universe itself continues to expand. This phenomenon stands in stark contrast to the interactions and clustering found in denser regions, where galaxies are tightly bound by powerful gravitational forces. Instead of being influenced by neighboring galaxies, the motion of galaxies within voids is largely determined by the expansive nature of the universe itself. Another intriguing aspect of cosmic voids is their relationship with dark matter. Dark matter, an invisible substance that interacts with gravity but not with light, plays a critical role in the formation of the universe's large-scale structure. In voids, where there is less visible matter, the density of dark matter is also reduced. This affects the gravitational influences in these regions, making the clustering of galaxies minimal. As a result, cosmic events in voids, such as the formation and movement of galaxies, are less influenced by local gravitational interactions and more governed by the general expansion of the universe. Furthermore, gravitational lensing offers astronomers another way to map and understand the elusive nature of cosmic voids. This phenomenon occurs when light from distant objects is bent around massive structures, such as galaxy clusters, due to their intense gravitational fields. By studying how light is bent in and around cosmic voids, astronomers can map the distribution of dark matter in these regions, providing further insight into the unseen forces that shape the universe. The relative emptiness of voids means that the bending of light is less pronounced than in regions with greater mass, making it even more crucial to study these phenomena to fully understand the hidden forces at play. In their quest to understand these vast, empty regions, astronomers are steadily peeling back the layers of mystery surrounding cosmic voids. Their research paints a more complete picture of the universe's structure, helping to refine our knowledge of how galaxies, dark matter, and cosmic forces interact. These studies also contribute to our understanding of cosmic evolution, shedding light on how the universe has developed and continues to unfold. The dynamics within cosmic voids offer a unique glimpse into the universe's less chaotic and more serene side. In contrast to the bustling and energetic activity seen in galaxy clusters, voids provide an almost peaceful setting where galaxies drift at their own pace. Yet, this serenity is not without its own significance. The relatively quiet, steady motion of galaxies within voids underscores the influence of the universe's expansion and highlights the forces that govern the entire cosmos. To put it in perspective, think of the universe as a sponge with both dense and empty regions. The dense parts are packed with galaxies, clusters, and other celestial bodies, while the empty regions, cosmic voids, are spread out like the holes within the sponge. Studying the universe often involves assuming a uniform, homogeneous structure, where galaxies and matter are distributed evenly across the vastness of space. However, the presence of these voids introduces a nuanced layer of complexity. As we look deeper into the cosmos, we begin to realize that these voids play a critical role in shaping the broader structure of the universe, challenging our earlier assumptions about its uniformity. Looking at the light emitted by distant galaxies, we see the effects of these cosmic voids. In areas where voids are prevalent, the scarcity of galaxies means that there is less light available. This can create a visual illusion of a universe with less structure, leading to potential misinterpretations about the isotropy, uniformity, and homogeneity of the universe. This effect becomes especially pronounced when examining gravitational lensing, where light from distant galaxies is bent around massive structures. In voids, where mass is less concentrated, the bending effect is less noticeable, complicating our understanding of the cosmos even further. As astronomers continue to study the large-scale structure of the universe, the discovery and analysis of cosmic voids challenge and refine our previous models. The study of these voids helps to deepen our understanding of how the universe functions, how galaxies cluster and spread, and how dark matter interacts with visible matter. They also underscore the importance of considering the intricacies of how the universe is organized, allowing scientists to update and improve their models of cosmic evolution. One of the most striking and powerful phenomena that astronomers study is the quasar, or quasi-stellar object, one of the most luminous energetic phenomena known to exist in the universe. These extraordinary objects are not stars at all, but rather the centers of galaxies that host supermassive black holes, whose masses range from millions to billions of times that of our sun. The immense energy radiating from quasars comes from the material surrounding these black holes. As gas and dust spiral toward the black hole in a process known as accretion, they heat up to extreme temperatures due to gravitational and frictional forces. This intense heat causes the gas to emit vast amounts of energy, often in the form of light across a wide spectrum, from radio waves to X-rays. What makes quasars particularly fascinating is their ability to outshine entire galaxies. The energy released when matter falls into a supermassive black hole can be trillions of times more powerful than the light produced by our sun. In fact, a single quasar can emit as much energy as thousands of galaxies combined. This colossal energy release offers a glimpse into the incredible efficiency of converting mass into energy, driven by the powerful gravitational field of the black hole. Quasars serve as essential tools for astronomers, offering insights into the early universe and the formation of galaxies. Their extreme brightness allows scientists to observe them from incredibly vast distances, shedding light on the conditions that existed billions of years ago. Imagine observing a distant lighthouse on a foggy night. The light you see is not just a beacon guiding the way, but a window into the past. Similarly, quasars provide a unique opportunity to study the early universe. These objects formed during a period known as the Cosmic Dawn, just a few 100 million years after the Big Bang, and they continue to serve as guides to understanding the universe's origins. Their light allows scientists to study the makeup of early galaxies, offering clues about how stars formed and the materials that make up galaxies. In a way, quasars are like time machines, offering a direct look into the universe when it was still in its infancy. Quasars also play a significant role in mapping the cosmic web, the vast and intricate structure of the universe. As light from quasars passes through the gas and dust scattered throughout space, it interacts with these intergalactic materials, allowing scientists to study the density and distribution of matter across the cosmos. This phenomenon is akin to shining a flashlight through fog. Not only does the light illuminate the surroundings, but it also provides important information about the density and distribution of particles in the air. Through this process, astrophysicists can piece together a timeline of galaxy formation, mapping how galaxies clump together across the vastness of space. In sum, both cosmic voids and quasars provide critical pieces of the puzzle in understanding the universe's evolution. These phenomena highlight the intricate forces that govern the cosmos, from the expansive nature of voids to the energetic brilliance of quasars, each contributing to our growing knowledge of the vast, complex universe we inhabit. Furthermore, the redshift observed in the light from quasars provides crucial insight into the rate at which the universe is expanding. This expanding universe context is vital for understanding not only the creation of new stars in ancient galaxies, but also the current influence of dark energy. Quasars are far more than just curiosities. They are central to our understanding of cosmic evolution and the early epochs of the universe. They serve as cosmic time capsules, offering a glimpse into the conditions that led to the universe we inhabit today. A quasar is a remarkable phenomenon, often hailed as one of the most luminous objects in the universe. At the core of each quasar lies a supermassive black hole, the engine driving its immense brightness. These black holes reside at the centers of distant galaxies, actively consuming the surrounding gas and dust. This intense feeding process generates an extraordinary amount of energy, radiating light so powerful that it can outshine entire galaxies. But the quasar's story doesn't end with this brilliance. Over time, the materials feeding the black hole may begin to deplete. As the black hole exhausts its immediate surroundings, its energy output drops significantly. Without a constant influx of fresh material, the quasar dims, becoming less active. Eventually, it enters a dormant state. The timeline of a quasar's active phase varies significantly. Some may shine brightly for millions to billions of years, while others may exhibit short bursts of luminosity before fading into obscurity. This variability suggests that a quasar's life cycle is not determined by a single factor. Instead, it is influenced by the rate at which the black hole consumes material and the availability of that material within its environment. Once dormant, quasars can remain in this subdued state for an exceedingly long period, potentially spanning billions of years, until conditions align to reignite their brilliance. During this dormant phase, the supermassive black hole remains quietly at the heart of the galaxy, waiting for cosmic conditions to once again fuel its insatiable appetite for material and, in turn, revive its powerful light. Quasars are among the most luminous entities in the cosmos, and their role in shaping our understanding of galactic structure and evolution cannot be overstated. When we examine the distribution of quasars across the universe, we find that they are predominantly located in regions that house massive galaxies. These galaxies, in turn, are actively growing, feeding their supermassive black holes, which release vast amounts of energy in the form of light that can travel across immense distances. Observations reveal that quasars are more frequently found at great distances from Earth, suggesting that many of them originated in the early epochs of the universe. This distribution reveals an intriguing trend. The farther away we look, the further back in time we are peering. The light from distant quasars has taken billions of years to reach us, enabling scientists to study the conditions of the universe when it was much younger, more dynamic, and more chaotic. The clustering of quasars offers valuable clues about areas where galaxy formation and evolution have been particularly active. By investigating their locations, researchers can uncover important insights into how galaxies and large-scale structures developed over time. The patterns in which quasars are distributed offer a fascinating glimpse into the universe's history, showcasing the immense influence of gravity in shaping cosmic structures. In regions where quasars are densely concentrated, there is often an environment rich in galaxies, suggesting that these regions may have been vital in the formation of the early universe. Quasars, then, do not just shine brightly. They serve as markers, signaling areas where gravitational forces have been particularly intense and where galaxy formation was particularly prolific. By studying these regions, scientists can piece together a more comprehensive understanding of the universe's formation, providing vital clues to the processes that have shaped it. At their core, quasars are driven by supermassive black holes, some containing masses ranging from millions to billions of times that of our Sun. As matter spirals inward toward the black hole, it forms an accretion disk, a rotating disk made of gas and dust. This accretion process is the primary source of a quasar's extraordinary luminosity. The material in the disk becomes intensely heated due to the immense friction and gravitational forces at play, emitting vast amounts of electromagnetic radiation. This radiation often exceeds the combined light emitted by the entire galaxy surrounding the black hole. Yet, despite our understanding of this fundamental mechanism, the full details of how such extreme radiation is produced remain a subject of intense scientific investigation. A significant area of mystery lies in the behavior of the accretion disk itself. While the basic principles are understood, scientists are still working to decipher how different temperatures and chemical compositions within the disk affect its behavior. Additionally, The rate at which material is funneled into the black hole plays a critical role in the overall luminosity of the quasar. Researchers are also exploring the mechanics of the jets that quasars often emit. These jets are powerful streams of particles shot out at nearly the speed of light from regions near the black hole. The jets are thought to be formed by the interaction of magnetic fields with the accretion disk, but the specific processes that govern their formation remain elusive. The formation of these jets, along with the exact physics involved, is an ongoing puzzle for astrophysicists. Understanding how these jets are propelled at such high velocities and why they exhibit such extraordinary power could reveal much about the forces at play near the black hole. Despite the progress made in recent years, much about the inner workings of quasars remains a profound mystery. What is clear, however, is that quasars are not just distant objects of curiosity. They are crucial to unlocking the secrets of the universe's early years and its ongoing evolution. Through the study of quasars, we gain more than just insight into the mechanics of black holes and accretion disks. We are granted a window into the very forces that shape galaxies, stars, and the universe as a whole. Each quasar, each burst of light, provides a snapshot of cosmic history, a history that continues to unfold across the vast expanse of space and time. Furthermore, the evolution of quasars across cosmic time raises profound and fascinating questions, inviting further exploration into the very fabric of our universe. These energetic beacons of light, which were first identified in the early universe, appear to thrive in the more distant reaches of space. Interestingly, we observe these phenomena primarily in the earlier epochs of the universe, a time when cosmic conditions were vastly different from what we see today. The relationship between the growth of supermassive black holes and the galaxies they inhabit remains an area of intense study. How do these immense black holes influence the evolution of their host galaxies? And in turn, how do galaxies shape the growth of these dark titans? What role do galactic mergers, interactions, and cosmic collisions play in this intricate dance of growth and development? As astronomers and astrophysicists probe deeper into the universe's history using increasingly advanced telescopes and observatories, each new discovery brings us one step closer to understanding the mechanics behind these distant, enigmatic objects. However, every new revelation about quasars only seems to raise more questions. Questions that beckon us to dive further into the unknown, to challenge our current models of the universe and to rethink what we know about the cosmos at large. This quest to fully understand quasars and their counterparts is not merely an academic pursuit. It is central to our understanding of the fundamental workings of the universe itself. Each quasar, with its brilliance and mystery, serves as a lighthouse in the dark, guiding us toward new insights about how galaxies form, evolve, and interact with one another in the grand cosmic tapestry. In a similar vein, fast radio bursts, FRBs, brief, intense bursts of radio waves originating from distant corners of the universe, have captured the imaginations of astronomers and astrophysicists alike. These bursts, which last only a fraction of a second, release an extraordinary amount of energy. In fact, each burst can emit as much energy as the sun does over several days. The immense energy and transient nature of FRBs make them particularly intriguing within the field of astrophysics, as their sudden, powerful flashes appear almost like cosmic fireworks, but their origins remain an elusive mystery. What sets FRBs apart from other cosmic signals is their speed and intensity. While phenomena such as supernovae or pulsars typically exhibit prolonged or cyclical emissions, FRBs stand out due to their singular, highly intense nature. The question that looms over these enigmatic bursts is, where do they come from and what drives them? Several theories have emerged, ranging from the possibility that they originate from magnetars, highly magnetized neutron stars, to more exotic possibilities, such as interactions with black holes or even the unthinkable, extraterrestrial technology. Despite the many hypotheses, the precise origins of FRBs remain a subject of intense research. Some of these bursts repeat, offering tantalizing clues that suggest a pattern, while others seem to appear just once, leaving us to wonder if these flashes are truly random or if they follow a more complex underlying mechanism. The distinct patterns of radio frequency emissions found in some FRBs only add to the intrigue. For example, some FRBs repeat at regular intervals, while others seem to flare up sporadically, offering scientists an invaluable glimpse into their mysterious nature. The uniqueness of these bursts fuels ongoing investigations, as astronomers and physicists endeavor to unravel not only the origins of FRBs, but also their role within the greater cosmic framework. Each discovery about these mysterious radio flashes opens the door to understanding larger cosmic events, perhaps even giving us clues about the fundamental structure of space-time itself. As we continue to study and probe deeper into these fleeting phenomena, we may eventually uncover revelations that reshape our understanding of the universe at its most fundamental level. Fast radio bursts, since their first discovery, have kept scientists on the edge of their seats, with their unpredictable nature and intense energy, leaving many in awe. While the early theories suggested a connection to highly violent cosmic events, perhaps related to collapsing stars or the explosion of supernova, new evidence has broadened our comprehension of these enigmatic signals. One of the key breakthroughs in this field has been the identification of a connection between certain types of FRBs and magnetars. Magnetars are extremely rare and fascinating celestial objects, rotating neutron stars with incredibly strong magnetic fields. Observations have shown that a specific type of FRB, characterized by its periodic repetition, aligns with the behavior of magnetars, suggesting that they might be responsible for at least some of these mysterious signals. The connection between magnetars and FRBs is not just an intriguing coincidence. It offers a plausible explanation for the extreme energy output observed in these bursts. The extraordinary magnetic fields of magnetars could, in theory, trigger the intense radio emissions seen in FRBs, offering a new pathway for understanding these remarkable phenomena. Additionally, studies have shown that certain FRBs appear to originate from regions of space with particularly dense interstellar material. This finding suggests that the environment surrounding these bursts might play a significant role in shaping the nature of the signals we receive. As researchers analyze the scattering of these radio waves, they have uncovered clues pointing to the presence of dense clouds of gas and dust that might be interacting with the radio signals, distorting them in unique ways. New telescope technologies and observational projects have played an instrumental role in advancing our understanding of FRBs. With the advent of more sensitive radio telescopes, scientists are now able to detect even fainter bursts, ones that might have been overlooked by older instruments. These modern telescopes utilize large arrays of antennas that work in concert, allowing them to gather data from a wide area of the sky simultaneously. This expanded observational capability has proven essential in tracking and studying these fleeting cosmic signals. Another groundbreaking advancement lies in the computational power of modern computers. Today, sophisticated algorithms can analyze vast quantities of data in real time, enabling astronomers to detect potential FRBs almost instantaneously. This rapid processing capability allows scientists to act quickly when an FRB is detected, ensuring that further observations can be made without delay. Furthermore, machine learning techniques have been employed to help distinguish between actual cosmic events and interference from noise, refining our understanding of these enigmatic bursts. The precision of modern timing techniques also plays a crucial role in FRB research. By synchronizing telescopes around the world, scientists can now pinpoint the exact location of an FRB with unparalleled accuracy. This enhanced precision enables researchers to trace the bursts back to their host galaxies, uncovering not only the origins of the bursts themselves, but also the environments in which they occur. By studying these environments, we are gradually piecing together the complex factors that contribute to the formation of these mysterious, high-energy bursts. As our understanding of FRBs continues to evolve, the mysteries surrounding them remain far from solved. Yet, with each new discovery, we gain a deeper appreciation for the complexity of the universe and the extraordinary events that unfold within it. The study of these fleeting bursts of energy, these enigmatic signals from distant galaxies, has already revolutionized our understanding of the cosmos. And as technology continues to advance, we are likely to uncover even more profound insights about the universe's most perplexing phenomena. Advancements in the design of observational programs have dramatically enhanced our ability to monitor the sky, allowing astronomers to explore the cosmos in ways previously unimaginable. With continuous monitoring coupled with dedicated surveys, the chances of detecting fast radio bursts, FRBs, which are inherently fleeting, have increased substantially. These bursts, known for their transient nature, present a unique challenge in astrophysical observation, as they appear so suddenly and vanish just as quickly. The application of sophisticated observational strategies has transformed the process of detecting FRBs from a rare, sporadic event to a systematic scientific endeavor. Today, astronomers can confidently track these elusive phenomena, contributing to a more comprehensive understanding of their origins and the forces that give rise to them. Furthermore, the integration of multi-wavelength observations, spanning radio, optical, and even gamma-ray data, has proven invaluable in enhancing our understanding of FRBs. This holistic approach, combining different observational techniques, provides a richer, more nuanced context for studying these bursts. By analyzing the bursts across the full electromagnetic spectrum, researchers can obtain critical insights into the physical processes that generate these extraordinary events. Each wavelength reveals different facets of the bursts, from their origins to the interactions they undergo during their journey through space. This multidimensional perspective not only broadens our comprehension of FRBs, but also helps scientists piece together the cosmic mechanisms that drive such phenomena. These advancements in technology and methodology form the backbone of future research on FRBs. As new instruments are developed and existing ones refined, astronomers are poised to unlock even deeper mysteries. The study of FRBs offers more than just a scientific curiosity. It provides a unique opportunity to probe the very fabric of our universe. With each new discovery, we move closer to understanding how these bursts fit into the broader cosmic landscape and how they relate to the larger processes that shape the cosmos. Fast radio bursts, FRBs, are among the most enigmatic phenomena in the universe. First detected in 2007, these brief yet powerful bursts of radio waves last only milliseconds but release an astounding amount of energy. In fact, the energy produced in that brief moment can rival the total energy emitted by the sun over the course of an entire year. Such incredible bursts, originating from deep space, have generated intense curiosity and speculation among astrophysicists. The question of their origins remains open, with various theories attempting to explain this phenomenon. One leading hypothesis suggests that FRBs may be the result of extreme astrophysical events, such as the merging of neutron stars. During such a merger, immense gravitational forces could create the ideal conditions for an FRB to occur. Neutron stars, themselves remnants of massive stars that have exploded in supernovae, possess extraordinarily dense cores and powerful magnetic fields. These extreme conditions could potentially generate the bursts of energy observed in FRBs. Another candidate for the source of FRBs is magnetars, a type of neutron star with exceptionally strong magnetic fields. Certain activities on or near their surfaces, such as massive flares, might produce intense bursts of radio waves similar to those seen in FRBs. However, the potential origins of FRBs are not limited to more conventional astrophysical phenomena. Some researchers have even proposed that FRBs could be linked to more exotic occurrences, such as the collapse of massive stars, or, more controversially, extraterrestrial technologies. While the latter theory is speculative and highly contentious, it nevertheless reflects the vast array of ideas being considered as scientists attempt to unravel the mystery of these elusive bursts. Despite the many theories, a definitive explanation remains elusive, and the search for answers continues. Another intriguing aspect of FRBs is their potential connection to the environments in which they occur. Research has shown that certain FRBs are localized to specific galaxies, and studying the host galaxies may reveal important clues about the nature of the bursts themselves. By analyzing the magnetic fields, the density of material, and other environmental factors within these galaxies, scientists can gain insights into how the conditions in these regions may influence the characteristics of the radio bursts. These findings suggest that the environment surrounding an FRB could play a significant role in shaping its behavior and appearance. Although we have yet to uncover the full story behind FRBs, ongoing research holds great promise for shedding light on their origins. Every new discovery brings us one step closer to understanding these phenomena, piecing together the larger cosmic puzzle. As technology continues to advance and our telescopes become more powerful, we are increasingly capable of observing and investigating these enigmatic bursts in greater detail. With each breakthrough, we edge closer to unraveling the profound mysteries surrounding FRBs and their role in the vast cosmic landscape. FRBs are not only fascinating due to their brief but intense nature, but also because they offer a unique window into intergalactic space. As these bursts travel across immense cosmic distances, they interact with the matter and energy that lie between their source and Earth. This interaction provides valuable information about the medium through which the bursts pass. For example, the way an FRB's signal changes in frequency as it moves through space can reveal crucial details about the density and distribution of the gas, dust, and other elements scattered throughout intergalactic space. Such variations in frequency, known as dispersion, occur as the signal interacts with the electrons and particles present in the intervening medium. The effect can be likened to how sound waves change as they travel through different atmospheric conditions. In the case of FRBs, studying these frequency shifts can help scientists map out the distribution of matter in regions of space that are otherwise difficult to observe. This makes FRBs not only important for understanding their own origins, but also a valuable tool for probing the universe's larger structure. Ultimately, the study of FRBs is more than just an exploration of a mysterious astronomical event. It is an exploration of the very nature of space itself, a journey into the heart of the universe's most extreme phenomena. As we continue to develop more advanced observational technologies and refine our understanding of these enigmatic bursts, we gain deeper insights into the processes that govern the cosmos. Each new discovery brings us closer to understanding the true nature of these celestial phenomena and their significance in the grand cosmic tapestry. Bees, small as they are, may hold the key to unlocking some of the greatest cosmic mysteries, including those surrounding the bursts of energy we see in deep space. These enigmatic signals, known as fast radio bursts, FRBs, could be linked to some of the most cataclysmic events in the universe, such as the violent collisions of neutron stars or the intense activity surrounding magnetars. Magnetars are neutron stars with incredibly strong magnetic fields, and their behavior could play a central role in these cosmic phenomena. Understanding the triggers of these bursts, whether they originate from star collisions or magnetar-driven events, offers invaluable insight into the life cycles of stars and the energetic processes that drive the evolution of galaxies. The ongoing study of FRBs gives us a lens through which we can observe the mechanics of cosmic evolution, helping scientists piece together the complex dynamics that have shaped the universe we see today. One of the most fascinating aspects of these bursts is their potential to act as probes for understanding the expansion of the universe. When these radio waves travel across vast stretches of intergalactic space, their signals are influenced by the very fabric of space-time, which is stretching as the universe expands. As these waves pass through expanding space, their properties can shift, providing us with a unique way to measure the cosmic growth. By studying the fluctuations in their signals across different distances, scientists are gaining valuable insights into the behavior of dark energy, an enigmatic force driving the accelerated expansion of the universe. These bursts, once thought to be fleeting and random, now appear to be much more than just transient signals. They are messages from the deepest corners of the cosmos, offering a window into the fundamental nature of space itself. Every new discovery about fast radio bursts sharpens our understanding of the universe's structure, pushing us to reconsider the very way we think about the cosmos and our place in it. Fast radio bursts are not alone in offering profound cosmic revelations. Gamma ray bursts, GRBs, another spectacular and incredibly powerful phenomenon, are among the most energetic events we observe in the universe. These bursts, which occur when massive stars meet their tragic end, release unimaginable amounts of energy. As these stars reach the final stages of their life cycle, they burn through their nuclear fuel and collapse under their own gravity, creating either a black hole or a neutron star. During this collapse, a torrent of energy is released, shooting out beams of gamma rays into the universe. These gamma rays, some of the most intense forms of electromagnetic radiation, travel across vast distances, bringing with them critical information about the processes that govern stellar evolution. Another scenario that can produce gamma ray bursts is the collision of two neutron stars. When these dense, compact objects spiral toward each other and ultimately collide, they release an astonishing amount of energy. The energy released in these events is so powerful that it can temporarily outshine entire galaxies. Such intense bursts of energy are brief but extraordinarily bright, offering astronomers a fleeting glimpse into one of the most dramatic processes in the universe. What makes gamma ray bursts truly remarkable is their sheer intensity. A single burst can release more energy in just a few seconds than our sun will produce over its entire lifetime. This extraordinary release of energy is a result of the extreme conditions present during these events: intense gravitational forces, rapid particle acceleration, and the crushing collapse of stellar material. Gamma ray bursts not only captivate us because of their unimaginable power, but also provide deep insights into the fundamental processes occurring during the universe's most violent and energetic events. The study of gamma ray bursts has significantly expanded our understanding of stellar life cycles and the catastrophic events that unfold at the end of a star's life. These bursts, which originate from massive stars, mark the final explosive chapter in the life cycle of these giants. When such a star exhausts its nuclear fuel, it can no longer sustain the internal pressure required to resist gravity. As a result, the star collapses, triggering a violent explosion known as a supernova. In some cases, this explosion can result in the formation of a black hole from which gamma ray bursts emerge. By studying these bursts, scientists have been able to unravel the mysteries surrounding the birth and death of stars, offering valuable clues about the complex processes that govern stellar evolution. Gamma ray bursts also help identify the types of stars that are likely to end their lives in this dramatic fashion. Through careful observation, astronomers have determined that certain massive stars, particularly those that have the potential to form black holes, are the prime candidates for generating gamma ray bursts. The exact conditions that lead to these catastrophic events are still being studied, but these bursts have already shed light on the nature of the stars involved and the violent transformations they undergo before their final explosion. Moreover, the afterglow of a gamma ray burst, visible across a wide range of wavelengths, provides further insights into the environment surrounding the explosion. This afterglow allows astronomers to examine the conditions that existed before the star's death and how the surrounding stellar material reacted to the event. In addition, it offers a glimpse into the larger galactic environment, helping scientists better understand how stars interact with their surroundings. The explosion of a massive star is not only a transformative event for the star itself, but also for the broader galaxy in which it resides, influencing the formation and evolution of other stars and planetary systems. Research into gamma ray bursts has also revealed their critical role in the metal enrichment of the universe. As these massive stars explode, they release heavy elements like iron, nickel, and oxygen, into the interstellar medium. These elements are crucial for the formation of new stars, planets, and even life itself. The explosion of a star, therefore, not only marks the end of that star's life, but also serves as a catalyst for the creation of new cosmic structures. The metal enrichment caused by gamma ray bursts plays an essential role in the evolution of galaxies, influencing the chemical composition of the universe and the future formation of stars and planets. Through the study of gamma ray bursts, scientists are peeling back the layers of one of the universe's greatest mysteries, the life cycle of stars. These bursts offer a glimpse into the birth, evolution, and death of the stars that populate our universe. Each discovery brings us closer to understanding how the universe's most violent events shape the night sky we observe today, shedding light on the fundamental processes that drive the ongoing evolution of galaxies, stars, and planets across the cosmos. Gamma ray bursts, GRBs, are among the most awe-inspiring and powerful phenomena in the universe, marking cataclysmic events of extreme energy that rival anything else in the cosmos. These bursts, which can release more energy in a few seconds than our sun will in its entire lifetime, are intrinsically linked to some of the most dramatic and final moments of a star's existence. Their origins are tied to the death throes of massive stars and the cosmic aftermath of neutron-star collisions, events that hold the key to unlocking some of the deepest mysteries of the universe. When a massive star reaches the end of its life, having exhausted its nuclear fuel, it undergoes a supernova explosion. This spectacular event is the star's final act, marking its violent demise. However, in certain cases, the implosion of the star can trigger a gamma-ray burst, creating a cataclysmic outpouring of energy. As the star's core collapses under its own immense gravitational pull, it forms a singularity, or a black hole. At the same time, it generates a highly energetic jet of particles that accelerates close to the speed of light, directing an intense stream of gamma radiation into space in a narrow beam. If Earth happens to be aligned with this beam, observers on our planet would witness an intense flash of gamma rays, one that could last mere moments but would be profoundly powerful. The sheer energy in such a burst is enough to outshine entire galaxies, albeit briefly. In contrast, another type of gamma ray burst arises from the collision of neutron stars. Neutron stars are the dense remnants of collapsed stars, with a mass similar to the Sun, but a radius no greater than a city. When two of these incredibly dense objects orbit each other closely, their paths inevitably bring them into a fatal collision. This violent merger produces not only gamma-ray bursts of short duration, but also leads to the formation of heavy elements like gold and platinum, which are scattered into the cosmos. The energy released during the collision powers massive jets of gamma radiation, creating a short but extremely intense burst. These neutron star mergers represent a fascinating and dangerous event in the universe, one that also contributes to the creation of some of the heaviest elements in existence. Both of these cosmic events, supernova explosions and neutron star collisions, illustrate the dynamic and interconnected nature of the universe, where the death of one star can ignite the birth of immense energy in another. They provide us with a glimpse into the intricate life cycle of stars and the complex physical processes that shape the evolution of galaxies, the formation of black holes, and the very makeup of the elements that constitute everything we know. Yet, gamma-ray bursts, as wondrous as they are not without their dangers. These bursts release an immense amount of energy in the form of gamma radiation, which is some of the most energetic radiation in the electromagnetic spectrum. If a gamma-ray burst were to occur too close to Earth, the radiation could have a devastating effect on our planet. The intense burst of gamma rays could disrupt the atmosphere, depleting the ozone layer and exposing life on Earth to harmful ultraviolet radiation. While the probability of a gamma-ray burst occurring within a dangerous proximity to Earth is incredibly low, the sheer scale of their power makes them a subject of scientific concern. At the same time, gamma-ray bursts offer remarkable opportunities for scientific discovery. These violent events provide an unparalleled window into the high-energy processes that occur in the universe. By studying them, scientists can gain a better understanding of the life cycles of stars, the conditions under which black holes form, and the behavior of matter under extreme gravitational and electromagnetic forces. The study of gamma-ray bursts also allows astrophysicists to test theories of fundamental physics, providing a unique environment to explore questions about the nature of matter, space, and time in some of the most extreme environments imaginable. Through careful observation and analysis of these bursts, we continue to refine our understanding of the universe's evolution and the forces that govern it. As much as gamma-ray bursts may remind us of the hazards lurking in the cosmos, they are also one of the clearest examples of how the universe challenges our knowledge, pushing us to learn more about the fundamental workings of space and time. They epitomize the duality of risk and reward that defines much of space exploration. While they present a potential threat to life, they also illuminate the vastness and complexity of the universe in ways that few other phenomena can. However, the study of gamma-ray bursts is not without its challenges. These events, though extraordinarily powerful, are incredibly rare, and their occurrence is unpredictable. A gamma-ray burst could occur at any time and anywhere in the universe, and Due to the vast distances involved, we may not even know it has occurred until millions or billions of years later when the light finally reaches us. When we observe a gamma ray burst, we are actually looking at the light from an event that may have taken place eons ago. The vast distances between us and these events complicate efforts to study them in real time, as much of the energy released during the burst will have dispersed by the time it reaches Earth. The cosmic distances involved also present difficulties in terms of how the gamma rays interact with the space between us and the source of the burst. As the rays travel through the universe, they are absorbed and scattered by the intergalactic medium, weakening the signal and making it harder for scientists to accurately analyze the burst. The energy involved in these bursts is so immense that even small fluctuations in the signal can make it challenging to capture all of the relevant data necessary to study these events in detail. On top of these observational challenges, scientists are still grappling with the fundamental mechanics that give rise to these powerful bursts. While we know that short-duration gamma-ray bursts are linked to the collisions of neutron stars, and long-duration bursts are connected to the collapse of massive stars, many of the exact processes that occur during these events remain a mystery. The extreme conditions involved, such as the immense gravitational forces and the high-energy physics at play, push the boundaries of our current understanding of physics. These phenomena challenge the very laws that govern our universe, raising new questions about how matter behaves in such extreme environments. Moreover, studying gamma-ray bursts requires highly sophisticated technology. Telescopes capable of detecting high-energy radiation, such as gamma rays, X-rays, and radio waves, have made significant advances in recent years, but they still face challenges in fully capturing the range of information needed to study these events in detail. Integrating data from different wavelengths, such as X-rays and radio waves, adds another layer of complexity, requiring advanced tools and techniques to interpret the data accurately. As scientists continue to improve both their observational tools and their theoretical models, the study of gamma-ray bursts remains a dynamic and rapidly evolving field. Each new discovery opens up new avenues of research, bringing us closer to understanding the fundamental processes that shape our universe. These bursts of energy, while fleeting, hold within them the potential to revolutionize our understanding of astrophysics, star formation, black holes, and the very fabric of space and time itself. Parallel to this, the cosmic microwave background, CMB, radiation is another critical piece of the puzzle in our quest to understand the universe. Often referred to as the echo of the Big Bang, the CMB represents the residual heat left over from the birth of the universe itself. In the aftermath of the Big Bang, the universe was a hot, dense, and rapidly expanding space. As it expanded, it cooled, allowing energy to condense into matter. However, the energy from that early universe didn't just vanish. It remains as a faint, pervasive glow filling the entire cosmos. Stretching and cooling over billions of years, this radiation has become detectable to us today as microwaves filling space uniformly in all directions. The study of the CMB provides crucial insights into the conditions of the early universe, offering a snapshot of its state when it was just a fraction of its current age. Tiny fluctuations in the temperature of the CMB give scientists a glimpse into the density of matter in the early universe, revealing patterns that help us understand the formation of galaxies, stars, and larger structures within the cosmos. By analyzing these temperature variations, scientists can trace the origins of cosmic structures, shedding light on how the universe evolved from its hot, dense beginnings to the vast and complex expanse we see today. The cosmic microwave background, just like gamma-ray bursts, serves as a tool for uncovering the hidden history of the universe. Both phenomena, though originating from vastly different points in time, are invaluable for understanding the fundamental processes that have shaped the universe, and they continue to inspire awe and wonder, pushing us to explore the vast, unknown territories of space and time. The existence of the cosmic microwave background, CMB, radiation, is one of the most compelling pieces of evidence supporting the theory of cosmic inflation. This theory proposes that the universe underwent an incredibly rapid expansion during its earliest moments, shortly after the Big Bang. The CMB itself is a vital relic from that time, a faint but persistent echo that offers a rare window into the very origins of everything we see around us today. As scientists explore this background radiation, it serves as a crucial time capsule, capturing a snapshot of the universe in its infancy. In our ongoing quest to understand the universe's vast history and its intricate evolution, a variety of cosmic backgrounds provide essential clues about its structure and the forces at play. Among these, the cosmic microwave background is perhaps the most famous, but it is far from the only one that holds vital information. Other less explored yet equally important cosmic backgrounds, such as neutrino and gravitational wave backgrounds, represent distinct but complementary pieces of the cosmic puzzle. By studying these different backgrounds, researchers can unravel the many layers of cosmic history, from the formation of matter to the behavior of celestial objects. Neutrinos, elusive subatomic particles, are produced in vast quantities during energetic cosmic events, such as supernova explosions or interactions involving cosmic rays. Because they interact so weakly with matter, neutrinos can travel through space virtually undisturbed, carrying valuable information from their sources across enormous distances. By studying the cosmic neutrino background, scientists can gain crucial insights into the processes that occurred in the early universe. This includes understanding the formation of matter, the behavior of stellar objects, and phenomena that would otherwise remain hidden from view. These invisible particles are like messengers from the past, revealing energetic events that helped shape the cosmos. On the other hand, gravitational waves, the ripples in space-time caused by some of the universe's most violent and energetic processes, have opened an entirely new frontier in astrophysics. These waves are generated by dramatic cosmic events, such as the collision of black holes or the merging of neutron stars. As these waves travel at the speed of light, they stretch and compress the very fabric of space itself. The detection of gravitational waves has revolutionized our understanding of the universe, allowing scientists to probe extreme environments and the population of massive cosmic objects. Gravitational wave backgrounds act as a complementary observational tool, filling in gaps left by traditional electromagnetic observations. By analyzing these ripples in space-time, scientists can explore the dynamics of celestial bodies and deepen our understanding of fundamental physics. Together, the study of neutrino and gravitational wave backgrounds adds a whole new dimension to our understanding of the universe's life cycle, from its explosive beginnings to the complex interactions of the fundamental forces at play. These cosmic backgrounds not only serve as valuable archives of cosmic information, but also challenge our existing models and inspire fresh ideas about the nature of reality itself. As we integrate these insights with observations from other cosmic phenomena, we are able to craft a more complete narrative of the cosmos, one that sheds light on its past while guiding our exploration of the future. The cosmic microwave background radiation is often regarded as one of the most profound remnants of the early universe. It provides a fascinating glimpse into the universe's infancy, offering crucial details about the conditions that prevailed just after the Big Bang. Despite decades of research, however, many mysteries surrounding this primordial soup of energy remain unsolved. One key focus for scientists has been mapping the tiny temperature fluctuations across this background radiation, which provide crucial insights into the early density of matter. These fluctuations are not just small variations in temperature, they are vital markers of where galaxies and clusters of galaxies would eventually form. Each fluctuation acts as a relic from a specific moment in time, providing us with a window into the early processes that led to the universe's structure as we know it today. Yet, many questions still remain unanswered. The precise mechanisms that led to the formation of galaxies and other large-scale structures in the universe are still elusive. For instance, while we know the universe's expansion is accelerating, the precise cause behind this acceleration remains one of the greatest mysteries in cosmology. This phenomenon is attributed to a force called dark energy, but the exact nature of dark energy remains unknown. The cosmic backgrounds, including the CMB, provide indirect clues about this mysterious force, but they cannot yet explain its origin or the way it drives the universe's expansion. Beyond these uncertainties, cosmic backgrounds also hint at the potential for interactions and phenomena beyond our current understanding of physics. Some theories suggest that our universe might not be the only one in existence. It could be part of a much larger multiverse. While such ideas are still speculative and lack definitive evidence, they provoke thought and challenge conventional wisdom. As research progresses, we may find that these cosmic backgrounds contain hidden traces of these interactions or even evidence of other universes, though such discoveries would require a radical shift in our understanding of the cosmos. There are also anomalies embedded within the cosmic background data that challenge conventional models of the universe. These unusual features could either signal new and unknown aspects of physics, or perhaps suggest errors in our measurements and interpretations. Regardless, they are an invitation to further explore the depths of the universe, and they push us to re-examine our assumptions about the nature of reality. The mysteries of cosmic backgrounds are far from resolved, and each new discovery raises more questions, offering tantalizing glimpses into what lies beyond our current knowledge. Cosmic backgrounds, in essence, are like ancient photographs of the universe at different stages of its development. They are invaluable records, capturing key moments in the life of the cosmos, and each one holds the potential to answer profound questions about the origins of everything we observe today. One of the primary cosmic backgrounds we study is the cosmic microwave background radiation. This faint glow, which fills the entire universe, originated roughly 300,000 years after the Big Bang, at a time when the universe cooled enough for light to travel freely. This moment marked a dramatic shift as the universe transitioned from an opaque fog into a transparent space, allowing this light to reach observers across time and space. By carefully analyzing the cosmic microwave background, scientists can derive important information about the early universe's conditions, such as its temperature, density, and the distribution of matter. The tiny fluctuations present in this radiation are especially significant because they provide clues about where galaxies would eventually form. These fluctuations are like cosmic breadcrumbs, marking the early stages of cosmic evolution and revealing the processes that contributed to the large-scale structures we observe today. In addition to the CMB, other cosmic backgrounds, such as the gravitational wave background, offer additional insights into the universe's evolution. These backgrounds capture high-energy events like the merging of black holes or neutron stars, which send ripples through space-time. Studying these ripples is a new frontier in astrophysics, helping scientists explore the universe's most energetic and dynamic processes. By examining these forms of background radiation, astronomers are able to piece together a timeline of cosmic history, detailing how galaxies, stars, and planetary systems came into existence. Future advancements in observational technology are set to revolutionize our understanding of cosmic backgrounds. Upcoming missions with cutting-edge detectors will allow us to peer deeper into space and time than ever before, potentially unlocking new insights into the universe's earliest moments. By examining the faintest signals from this early era, scientists will be able to uncover more about the conditions that shape the universe as we know it today. These future telescopes and missions will employ a range of wavelengths from radio to optical and infrared to study the universe from multiple angles. Infrared observations, for example, will allow us to see galaxies hidden behind cosmic dust, while radio frequencies will help reveal the processes that govern the formation of cosmic structures. By combining these diverse observations, scientists will be able to build a more complete picture of the universe's evolutionary history, from its fiery birth to its present state and beyond into the future. As we continue to explore the cosmos, the study of cosmic backgrounds will remain a cornerstone of our understanding of the universe. These faint afterglows, remnants of pivotal cosmic events, are not only vital pieces of evidence for the history of the universe, but also crucial tools for predicting its future. Through continued exploration and technological innovation, we can expect to unlock even more secrets, revealing the hidden stories that lie deep within the cosmic background radiation. Advancements in technology, particularly with tools like adaptive optics and increasingly larger apertures, are transforming the way we observe the cosmos. These innovations are directly addressing one of the greatest challenges in astronomy, the distortion caused by Earth's atmosphere. Historically, this atmospheric turbulence has blurred the sharpness of distant stars and galaxies, making it difficult to capture clear, high-resolution images. However, with new technologies in place, astronomers can now look beyond this limitation, enabling them to capture far more detailed and precise images of the universe. This leap forward promises more than just sharper visuals. As we gain the ability to observe with greater clarity, we open doors to uncovering subtle variations in the cosmic background radiation. These variations, tiny as they might seem, could reveal vital information about the fundamental processes that govern the birth of the universe. Specifically, they may provide crucial insights into primordial fluctuations, minute imbalances in energy that occurred fractions of a second after the Big Bang, offering us a window into the earliest stages of the cosmos. We are entering a new era of astronomical exploration, where the synergy between groundbreaking telescopes and innovative missions could not only enhance our understanding of the universe's background, but also propel us into unforeseen realms of discovery. It is possible that, along with answering existing questions, we may uncover entirely new phenomena, challenging long-held theories and reshaping our understanding of cosmic structures. As these efforts continue, they will bring us ever closer to answering some of the most profound questions about the nature of the universe, its vitality, the processes behind the formation of galaxies and other structures, and perhaps even the existence of regions in the cosmos that are entirely unknown to us. One such area of ongoing investigation is the search for a potential ninth planet in our solar system. For years, astronomers have speculated about the existence of a massive, as yet undetected planet lurking in the outer reaches of the solar system. Often referred to as Planet 9, this mysterious object has been theorized to exist based on the gravitational effects it appears to exert on the orbits of distant celestial bodies. These bodies, known as trans-Neptunian objects, TNOs, follow orbits that are both eccentric and highly inclined compared to those of the known planets. The clustering of these TNOs in particular patterns suggests that there may be an unseen force influencing their movements, possibly the gravity of a large, undiscovered planet. The theory posits that Planet 9 would be a world larger than Earth, but smaller than Neptune. It would reside far beyond the current known planets, with an orbit so elongated that it spends much of its time in the distant, cold reaches of the solar system. Its presence could explain the unusual orbits of TNOs, as its gravitational pull may help align their paths in ways that current models cannot easily account for. This hypothesis opens up fascinating questions about the structure and evolution of our solar system, particularly regarding the dynamics of its outermost regions. Another intriguing theory suggests that Planet 9 may be a remnant from the solar system's formative years. Early in the solar system's history, there might have been other large planets that were ejected from the system through violent gravitational interactions. Planet 9 could be one such survivor, an object that was flung outward, possibly reshaped by the chaotic forces at play during the system's infancy. This theory would add another layer to our understanding of how the solar system evolved, suggesting that not all the planets we see today formed in their current locations, and that some may have been displaced or lost altogether. The hunt for Planet 9 is ongoing, and while no direct observation of the planet has yet been made, astronomers are using advanced telescopes to peer into the farthest reaches of space, looking for evidence of this elusive world. By studying the gravitational effects on nearby celestial bodies, scientists hope to pinpoint the planet's location and better understand its nature. This search is not merely about finding a new planet. It is also about exploring the deeper forces at work in the outer solar system, gaining insight into the dynamics that shaped the planets we see today. Beyond the quest for Planet 9, another fascinating aspect of our solar system lies in the mysterious trans-Neptunian objects, TNOs, themselves. These icy bodies, located in the distant reaches beyond Neptune, follow highly irregular orbits, which often appear to defy simple explanations. Some of these objects have highly eccentric paths, while others follow trajectories that seem completely at odds with the motion of the main planets. These oddities have long intrigued astronomers, raising questions about the forces that govern the outer solar system. The bizarre orbits of TNOs may indicate that there are unknown forces, or even unseen celestial bodies, exerting gravitational influence over them. Planet 9, as previously discussed, is one such potential force, but there may be other factors at play as well. These irregular paths suggest that the early solar system was a far more chaotic place, one where the gravitational influence of large bodies, possibly even in collisions, shaped the trajectories of smaller objects. Scientists theorize that TNOs might have been scattered outward by the gravitational pull of the forming planets, or even displaced by collisions with other celestial bodies. The study of TNOs and their peculiar orbits offers a rare opportunity to explore the early solar system's dynamics. As researchers continue to track these objects, they uncover fascinating clues about how the solar system evolved over billions of years. Every unique orbit tells a story, offering hints about the forces at play during the solar system's infancy, forces that might challenge our current understanding of planetary formation and celestial mechanics. As we venture farther into the farthest reaches of our solar system, the challenges grow more significant. The Kuiper Belt, a vast region filled with icy bodies and dwarf planets, lies just beyond Neptune. While the Kuiper Belt is rich with potential insights into the early solar system, it also presents significant observational challenges. The objects here are faint, and the region itself is dark and cold, making it difficult for even the most powerful telescopes to detect all of its contents. Mapping and studying the objects in this region is an immense task, one that requires not only the best technology, but also innovative strategies to overcome the limitations of distance and darkness. Farther still lies the Oort cloud, a largely invisible region thought to surround the solar system. This massive spherical cloud of icy objects and potential comets exists at such a great distance from the Sun that it remains almost entirely hidden from current observational tools. While indirect methods like studying comet trajectories have provided clues about the Oort cloud's existence, it remains largely an enigma. The objects in the Oort cloud are faint and scattered across vast stretches of space, making them incredibly difficult to observe and study directly. Moreover, the dynamic nature of these distant regions adds another layer of complexity. Objects in both the Kuiper Belt and the Oort cloud are constantly in motion, influenced by gravitational interactions with other bodies, including those within our own solar system and even nearby stars. These interactions can alter the paths of these objects, complicating efforts to understand their origins and evolution. Many of the bodies in these distant regions are thought to have formed in different parts of the solar system, and their movements could reveal important clues about the solar system's early history. But tracking these movements accurately is a monumental challenge. In conclusion, the study of our solar system's outermost regions, the Kuiper Belt, Oort cloud, and the search for Planet 9, offers us a glimpse into the complex forces that have shaped our cosmic neighborhood. As we continue to refine our observational techniques and expand our understanding of these distant bodies, we are not only uncovering new objects, but also rewriting the story of our solar system's formation and evolution. The journey into these unknown realms is one that promises to challenge our current theories and deepen our understanding of the universe's grand design. Exploring the outer reaches of our solar system is not just a scientific endeavor. It is a monumental undertaking requiring years of meticulous planning and execution. The missions designed to explore these distant regions are fraught with incredible challenges. The probes sent on these journeys must be equipped to endure the harshest of environments, ranging from intense radiation to bone-chillingly low temperatures, and spanning vast distances that can stretch the duration of travel to many years, sometimes even decades. Each mission carries inherent risks, yet it is through these risks that we venture into the unknown, uncovering glimpses of distant worlds and the secrets they hold. However, the data returned from these missions is rarely conclusive. Instead, it offers just a fleeting window into the far-off realms that exist at the edge of our solar system. The exploration of the Kuiper Belt and the Oort cloud, two of the most enigmatic regions in space, presents a unique set of challenges. These regions are not only technologically difficult to study, but also inherently mysterious due to their distance and dynamic nature. Each obstacle encountered during these missions presents an opportunity for innovation. Scientists continue to develop new technologies and methodologies, striving to expand our understanding of these vital areas of our solar system. Through these efforts, we uncover more about the cosmic past, the formation of our solar system, and the underlying processes that govern celestial bodies. Comets and asteroids, especially those located in the outer regions of our solar system, serve as cosmic time capsules, preserving the conditions from the earliest days of the solar system. These objects, which have remained relatively unchanged over billions of years, offer scientists a unique opportunity to peer into the past. When these ancient bodies formed in the early solar system, they did so under conditions vastly different from what we observe today. Analyzing the composition of comets and asteroids gives us critical insights into the materials that were present during the birth of our solar system, roughly 4.5 billion years ago. The composition of these objects often includes ice, dust, and organic compounds, remnants of the primordial clouds that gave birth to our sun and the planets around it. The study of these materials allows scientists to reconstruct the conditions of the early solar system, shedding light on the processes that led to the formation of planets, moons, and other celestial bodies. The proportions of these ingredients, ice, dust, and organic compounds, can tell us much about how the planets developed and evolved over time, providing critical clues about the history of our cosmic neighborhood. Furthermore, the orbits of these objects provide valuable insights into the dynamic processes that have shaped the structure of our solar system. As comets and asteroids traverse the vast reaches of space, they often interact with the gravitational fields of nearby planets, altering their trajectories. These interactions reveal the subtle yet powerful forces that have influenced the movement and distribution of these objects over billions of years. By tracing the paths of these objects backward in time, scientists can infer the gravitational interactions that have shaped their current positions, offering a deeper understanding of the complex gravitational dance that governs our solar system. The history of impacts on Earth is intimately linked to the movements of asteroids and comets. Over millions of years, these spacefaring objects have collided with our planet, sometimes triggering dramatic changes to the environment. These impacts have had profound effects on Earth's atmosphere, climate, and even the course of life itself. Understanding the history of such impacts helps scientists gauge Earth's resilience to cosmic events and assess its vulnerability to future collisions. In studying these impacts, we learn not only about the forces that have shaped our planet, but also about the potential risks posed by these objects in the future. When we study comets and asteroids, we are not simply examining individual celestial bodies. We are uncovering a broad narrative of our solar system's history. This narrative includes the origins of planetary bodies, the evolution of planetary environments, and the enduring influence of celestial mechanics. Each discovery, each piece of data plays a crucial role in piecing together the complex puzzle of our solar system's formation and evolution. Spacecraft missions like New Horizons have been instrumental in revealing the secrets of our outer solar system. By venturing to distant celestial bodies that have never before been visited by human-made probes, New Horizons offers a unique opportunity to study regions and objects that remain largely unexplored. Think of New Horizons as a scientific scout sent to areas beyond the reach of our most powerful telescopes, offering a closer look at distant objects that can reveal much about the early days of our solar system. Launched nearly a decade ago, New Horizons made history with its landmark flyby of Pluto, a dwarf planet that had long been relegated to the status of not a planet. What it discovered was a world far more complex than anyone had imagined. The icy mountains, vast plains, and evidence of possible weather patterns on Pluto challenged long-held assumptions about the nature of distant worlds. These findings sparked new questions about the formation and evolution of the Kuiper Belt, a region extending beyond Neptune and filled with icy bodies like Pluto. Since that historic flyby, the mission has continued to explore other objects in the Kuiper Belt, offering insights into the building blocks of our solar system. Each encounter with these distant worlds provides scientists with invaluable information about the composition, atmosphere, and potential for past or present activity on these moons, dwarf planets, and other objects in the outer solar system. These missions act as time machines, allowing us to peer back into the early history of the solar system. By studying these distant objects up close, we gain a clearer understanding of how planetary systems evolve over time. We also deepen our understanding of the conditions that might support life beyond Earth, offering a glimpse into the potential for life elsewhere in the universe. The revelations brought forth by missions like New Horizons are just the beginning. The data gathered so far has set the stage for future explorations that will continue to reshape our understanding of the cosmos. These missions promise to unveil even more secrets about the solar system's past and help us refine our theories about planetary formation and evolution. Beyond our own solar system, astronomers have discovered a myriad of exoplanets, some of which defy our expectations and challenge our understanding of planetary formation and the potential conditions for life. Among these exoplanets, some stand out due to their peculiar and, at times, bizarre characteristics. One of the most fascinating examples is the hot Jupiter, a massive gas giant that orbits incredibly close to its parent star, resulting in scorching temperatures. The sheer contrast between the planet's size and its proximity to its star raises intriguing questions about how such a planet could form in the colder, outer regions of a solar system and then migrate inward toward the star. Another remarkable discovery is the so-called diamond planet, a world believed to be rich in carbon. Under the right conditions, the carbon on this planet could crystallize into diamond, creating an entirely new kind of celestial body. The idea of a planet made primarily of diamonds has captivated scientists, not only because of the unexpected materials involved, but also because it suggests that planetary systems can host a variety of chemical processes that are vastly different from those we see in our own solar system. Then there are planets that experience extreme and chaotic weather patterns, with temperatures so high they are capable of melting metals. These planets are thought to have atmospheres filled with clouds of molten glass, which are swept across the surface by powerful winds. Such hostile and unpredictable environments challenge our traditional views of what constitutes a habitable world, forcing us to reconsider the diverse range of atmospheres that may exist throughout the universe. These findings continue to expand our understanding of planetary formation and the conditions that may exist on planets in other star systems, adding layers of complexity to the search for life beyond Earth. The exploration of exoplanets, planets that orbit stars beyond our sun, has taken humanity into uncharted territories, revealing stunning and perplexing worlds that challenge our understanding of the universe. Among the most captivating of these are the circumbinary planets, which orbit 2 stars instead of 1. These unique worlds, which experience dual sunsets, offer an environment unlike anything we can find on Earth. Imagine a sky painted by 2 setting suns, creating breathtaking scenes that stir both wonder and scientific curiosity. However, these celestial oddities raise significant questions about their stability. With 2 gravitational forces at play, the potential for chaos in such complex systems is high. Could life thrive in such an extraordinary scenario where the very environment seems to be constantly in motion? What excites scientists about circumbinary planets is not just the exotic characteristics of these distant worlds, but the profound implications of their existence. Each new discovery forces researchers to rethink established theories in planetary science, particularly when it comes to habitability. Are the assumptions we've made about life's potential constraints too narrow? These planets, with their unusual dynamics, suggest that life might find a way to survive under conditions we have yet to fully comprehend. Their existence broadens the scope of possibilities in the search for life beyond Earth, inspiring scientists to dive deeper into questions about the nature of planetary systems and their potential for hosting life. Equally revolutionary in our quest to understand these far-flung worlds are the 2 primary methods used to detect and study exoplanets: the transit method and radial velocity technique. These groundbreaking approaches have expanded our knowledge exponentially, offering new ways to observe planets that orbit distant stars. The transit method works by detecting a slight dimming of a star's light when a planet passes in front of it from our viewpoint. This seemingly small dip in brightness contains vital information about the planet's size and orbital period. By studying the amplitude and duration of this dimming, scientists can estimate important features of the planet, such as its diameter and its distance from the host star. Each transit offers a unique glimpse into the nature of these distant worlds, revealing not just their size, but their position within their star's habitable zone, the region where liquid water could potentially exist. This is crucial in determining whether the planet could host life as we know it. The radial velocity method, on the other hand, focuses on the gravitational interactions between a star and its orbiting planet. As a planet moves through space, its gravitational pull causes the star to wobble, a subtle shift detectable through changes in the star's light. When the star moves toward Earth, its light shifts toward the blue end of the spectrum. When it moves away, the light shifts toward the red. By analyzing these shifts, astronomers can deduce the planet's mass, orbital shape, and distance from its star. The combined use of these two methods provides a more complete understanding of exoplanets, offering a deeper look into their potential for habitability. While the transit method tells us about the planet's size and position relative to its star, the radial velocity technique reveals its mass, a key factor that influences many aspects of a planet's environment, from gravity to atmosphere. As technology improves, scientists are able to detect smaller, more distant planets, expanding the boundaries of what is possible in exoplanet research. These advancements not only deepen our understanding of planets in distant solar systems, but also help us question the very formation of our own solar system, pushing us to consider the diverse possibilities for life beyond Earth. One particularly intriguing exoplanet is Proxima Centauri b, located just over 4 light-years away from our solar system. Positioned within the habitable zone of its star, Proxima Centauri b is at the perfect distance where conditions might allow liquid water to exist, a key ingredient for life as we know it. The fact that this planet exists so close to us makes it an ideal target for future exploration. Unlike other exoplanets that may be hundreds or even thousands of light-years away, Proxima Centauri b's proximity means that we could feasibly reach it within a human lifetime, given the right technology. What makes Proxima Centauri b even more intriguing is the possibility that it could have rocky characteristics similar to Earth. This opens up exciting possibilities about the planet's potential to support life. The star it orbits, a red dwarf, is much cooler and less luminous than our Sun, which means the planet would experience a different kind of climate, potentially one more conducive to life. This cooler environment also means that the planet's atmosphere, if it exists, might be very different from ours. Researchers are particularly interested in whether Proxima Centauri b's atmosphere could contain gases like oxygen or methane, molecules that are often associated with biological processes on Earth. In the coming decades, Proxima Centauri b could become a prime candidate for exploration, possibly through missions utilizing advanced propulsion technologies like light sails. These sails, propelled by powerful lasers, could allow spacecraft to reach the planet in a fraction of the time it would take using conventional methods. Such missions would not only focus on mapping the planet's surface, but also on studying its atmosphere and searching for signs of life. If we can overcome the technological challenges involved, Proxima Centauri b could become a crucial stepping stone in humanity's search for life beyond our solar system, offering us a glimpse into the possibilities of extraterrestrial life and the future of interstellar exploration. The discovery of exoplanet atmospheres has dramatically shifted the way scientists think about habitability. For many years, astronomers focused on identifying planets within the so-called habitable zone of their stars, a region where temperatures might allow liquid water to exist. The prevailing theory was that if a planet was in the right temperature range, it could potentially support life. However, as we began to detect the atmospheres of exoplanets, a more complex picture emerged. Atmospheres, it turns out, are crucial to a planet's ability to support life. An atmosphere can shield the planet's surface from harmful stellar radiation, regulate temperature through greenhouse effects, and even provide the necessary chemicals for life. The discovery of gases like oxygen, methane, and carbon dioxide in an exoplanet's atmosphere can provide vital clues about its potential to harbor life. For instance, the presence of methane and oxygen together could suggest biological processes at work, as these gases are typically produced by living organisms on Earth. Scientists have used spectroscopic techniques to analyze that filters through an exoplanet's atmosphere during transits. This light, which passes through the planet's atmosphere on its way to Earth, contains a wealth of information about the composition of the atmosphere. By studying this light, researchers can identify specific molecules present, helping to paint a picture of the planet's environment and potential for habitability. The discovery of water vapor or complex organic molecules could be game changers, providing tantalizing evidence that life might be possible in far-off worlds. As our understanding of exoplanets and their atmospheres deepens, we are beginning to realize just how diverse and complex these distant worlds can be. The hunt for habitable exoplanets is no longer just about finding planets in the right location around their stars. It's about understanding the intricate interplay between a planet's size, its atmosphere, and its potential to support life. The more we discover, the more we realize that the universe is far stranger and more wondrous than we ever imagined, offering endless possibilities for life beyond Earth. The study of exoplanet atmospheres is transforming the way we understand the potential for life beyond Earth. It has become clear that a planet's surface conditions alone do not tell the entire story of habitability. For example, a planet with a thick atmosphere might experience surface temperatures too extreme for life as we know it. In contrast, another planet with a thinner atmosphere might offer the perfect conditions for liquid water, which is essential for life. The atmosphere plays a critical role as a mediator in habitability, influencing whether a planet's environment is capable of sustaining life. This new understanding is reshaping the search for life in the cosmos. It pushes scientists to think beyond simply identifying the right location in the universe, and instead consider the complex interplay of factors that make a planet habitable. It forces a broader view, acknowledging that planets with very different atmospheric conditions might still harbor life. This approach expands the scope of our search, encouraging exploration into planetary environments that may not be Earth-like but still have the potential to support life. Ultimately, these discoveries suggest that the likelihood of finding habitable planets and perhaps life could be far greater than we ever imagined. However, the detection of life on exoplanets remains an incredibly difficult task, one that demands significant advancements in technology and new strategies in our scientific approach. The first major hurdle is the need for more powerful telescopes. Current instruments can detect exoplanets, but they struggle to gather enough detailed information about their atmospheres. The key to unlocking these secrets lies in developing space-based telescopes capable of capturing the faint light that passes through an exoplanet's atmosphere. This light carries critical information about the chemicals present in the atmosphere, revealing clues that could indicate the presence of life. Alongside advancements in telescope technology, improved spectroscopy techniques are essential. Spectroscopy allows scientists to analyze the light emitted or reflected by distant planets to determine their atmospheric composition. The ability to detect molecules like oxygen or methane would be groundbreaking, as these gases are often associated with biological processes here on Earth. By analyzing light across a broader range of wavelengths, scientists can improve their chances of identifying molecules that suggest the presence of life. These advancements in spectroscopic technology, combined with powerful telescopes, will significantly enhance our ability to detect life on distant worlds. Equally important is fostering international collaboration and pooling resources from different nations to develop new space missions. When countries work together, they can combine their unique expertise and technologies, creating telescopes and instruments capable of peering deeper into the universe. Such collaboration accelerates the pace of discovery, ensuring that scientific progress is not constrained by national borders. In parallel, the development of artificial intelligence and machine learning will play a crucial role. These technologies can help sift through vast amounts of data from telescopic observations, identifying patterns and potential biosignatures more quickly and accurately than human analysis alone. Additionally, ongoing research into the conditions that sustain life on Earth will guide our search for life elsewhere. By understanding the fundamental factors that make Earth habitable, scientists can narrow their focus to those environments most likely to support life. One of the key criteria is a planet's location in its star's habitable zone, where conditions might be right for liquid water to exist, an essential ingredient for life as we know it. As this research progresses, it becomes increasingly clear that life may exist in places we never expected, in environments vastly different from Earth. Finally, the long-term sustainability of funding and support for these ambitious projects is essential. By securing consistent resources and creating supportive frameworks for research, the global scientific community can continue to pursue groundbreaking discoveries. With each technological advancement, each new space mission, and each collaboration between nations, we move one step closer to answering the profound question, are we alone in the universe? In the pursuit of this answer, every breakthrough is a stepping stone. As our understanding deepens, we may come to realize that life on other planets is not as rare as once believed. The universe could very well be teeming with life, just waiting for us to uncover it. Parallel to this search for life, there exists the fascinating field of galactic archaeology, which seeks to unravel the history of our Milky Way galaxy. Much like traditional archaeology reveals the stories of human civilizations, galactic archaeology helps us decipher the cosmic history embedded within stars, gas, and dust. The Milky Way, in this sense, acts as a massive time capsule, containing the remnants of billions of years of cosmic evolution. Each star within the galaxy carries a story, its chemical composition reflecting the conditions of the early universe and the processes that have shaped its environment. Stars form from the gas and dust present in their surroundings, and as they age, they undergo nuclear fusion in their cores, creating heavier elements. These elements are then scattered across space when many stars explode in supernova events. This process enriches the interstellar medium, seeding it with the building blocks of future generations of stars and planets. By studying the chemical composition of stars in different regions of the galaxy, scientists can trace the timeline of element creation, revealing insights into the history of star formation, supernova explosions, and even the interaction between galaxies. In particular, the oldest stars, often found in the galaxy's halo, offer a glimpse into the conditions of the early universe. These ancient celestial bodies have witnessed the formation of the Milky Way and can tell us about the processes that led to its creation. By analyzing the light from these stars, researchers can piece together the galaxy's story, learning how it grew and evolved over billions of years. The chemical compositions of stars as essential clues in this grand narrative. For instance, stars that formed from primordial material, mainly hydrogen and helium, are considered metal poor, as they contain little of the heavier elements forged in later generations of stars. Younger stars, on the other hand, contain higher levels of these elements, suggesting that they formed from gas clouds enriched by earlier generations of stars. This stellar chemistry provides a window into the past, helping scientists map out the evolution of the Milky Way and its neighbors. The study of galactic archaeology also focuses on the movements of stars throughout the galaxy. Some stars travel on erratic orbits, indicating that they may have originated in other galaxies or been influenced by galactic events, such as mergers. By tracking these stars' movements, scientists can reconstruct the Milky Way's past interactions with neighboring galaxies. These cosmic collisions and accretions have played a vital role in shaping the Milky Way's structure and starry composition. Perhaps the most intriguing aspect of galactic archaeology is understanding the Milky Way's interactions and mergers with other galaxies. Over the course of its existence, the Milky Way has absorbed smaller galaxies, reshaping its structure and contributing to the starry landscape we see today. These smaller galaxies, in essence, serve as building blocks, providing fresh material for star formation and altering the galaxy's dynamics through gravitational interactions. Yet, Despite our advances, the precise number and identities of the smaller galaxies that have merged with the Milky Way remain largely unknown. This leaves significant gaps in our understanding of the galaxy's history. However, the ongoing study of galactic archaeology promises to gradually fill these gaps, providing a more complete picture of the Milky Way's past, present, and future. The story of the Milky Way is still being written, and with every discovery, we move closer to understanding the vast, complex history of our galaxy and its place within the larger universe. This cosmic detective work through the study of stars, gases, and collisions holds the key to answering some of the most profound questions about the formation of galaxies, the evolution of our universe, and the possibility of life beyond Earth. Moreover, every galaxy merger generates incredibly complex gravitational waves and triggers bursts of star formation as the gas and dust from the merging galaxies collide. This chaotic collision can lead to the birth of new stars in regions of space that were previously quiet and devoid of significant activity. However, not all mergers are a harmonious process. Some can disrupt the orbits of stars, causing chaotic and unpredictable distributions of stars and other forms of matter within the galaxies. A prime example of this chaotic aftermath can be seen in the distinctive halo of stars that surrounds our own Milky Way galaxy. This halo is not just a random scattering of stars, but rather it offers critical clues to the galaxy's turbulent past, hinting at a history of violent encounters and mergers that continue to influence its behavior and structure even today. In addition to visible matter, an even more enigmatic substance plays a crucial role in these galactic mergers: dark matter. Dark matter, an invisible and elusive substance that makes up a significant portion of the universe's total mass, interacts with galaxies during collisions in ways that remain a mystery to scientists. As galaxies merge, they interact not only through the visible matter that we can observe, such as stars, gas, and dust, but also through dark matter, which is undetectable by traditional means. Investigating the way dark matter interacts and reshapes the distribution of matter within and around the Milky Way could unlock profound insights, not just about our galaxy's formation and evolution, but also about the very nature of the universe itself. The history of the Milky Way's mergers is inextricably linked to our understanding of its future. Projections of the galaxy's eventual fate indicate that, in several billion years, it will undergo a slow-motion cosmic encounter with the nearby Andromeda galaxy. This collision, though still far in the future, is expected to reshape both galaxies. While the exact details of this event remain cloaked in uncertainty, scientists cannot yet predict every twist and turn of this galactic drama. Studying past merger events provides us with invaluable insight into what we might expect. By tracing the Milky Way's history of mergers, we are better equipped to anticipate the larger-scale changes and phenomena that will occur as our galaxy continues to evolve over time. This dynamic narrative is not just a record of past events, but also a prelude to the cosmic ballet that will continue to unfold, stretching far into the future. One of the most fascinating ways to trace this evolution is through the study of star clusters. Star clusters are often likened to cosmic time capsules, preserving key snapshots of the universe's history. These clusters come in two primary forms: open clusters, which are loosely bound groups of young stars that reside in the spiral arms of galaxies, and globular clusters, which are dense spherical collections of older stars that orbit the galactic core. The age of a star cluster provides crucial information about the time period in which its stars formed, acting as a cosmic photograph of a specific era in the universe's evolution. Globular clusters, in particular, are among the oldest objects we can observe in the universe. These ancient clusters are believed to contain the oldest surviving stars, dating back to a time when the universe itself was still young. By studying these stars, astronomers gain critical insights into the conditions that existed in the early universe and the processes that led to the formation of galaxies. On the other hand, the stars in younger open clusters are more likely to contain heavier elements, which were formed through nuclear processes in previous generations of stars. This variation in the chemical makeup of stars offers a powerful window into the ongoing process of stellar evolution, showing how stars recycle materials from older generation, enriching the interstellar medium in the process. Furthermore, The distribution and movement of star clusters provide important clues about the way galaxies form and grow. For example, the spread of star clusters throughout a galaxy can inform researchers about the galaxy's internal gravitational interactions. Additionally, by studying the trajectories of star clusters, astronomers can infer the presence of dark matter, the unseen mass that governs the behavior of galaxies but eludes direct detection. Star clusters are thus not just isolated objects in space. They are key pieces of evidence that reveal how galaxies evolve over billions of years. Through these stellar fossils, we gain a deeper understanding of the ongoing processes that have shaped and will continue to shape galaxies, including our own. These clusters reflect different stages of galactic evolution, providing a glimpse into the forces and events that have sculpted the cosmos. Together, they form a dynamic and complex story of our universe's past, offering essential clues about how galaxies like the Milky Way came to be. Looking forward, the future of galactic archaeology is deeply intertwined with cutting-edge technologies and missions that will revolutionize our understanding of the universe's history. One of the most promising developments in this field is the next generation of space telescopes. With their advanced optics and unparalleled sensitivity, these telescopes will be able to peer deeper into the cosmos than ever before. By capturing the faint light from distant stars and galaxies, these instruments will reveal hidden details about the formation of the first stars and galaxies, shedding light on the conditions that prevailed in the early universe. In addition to these revolutionary telescopes, upcoming space missions focused on surveying our own galaxy, the Milky Way, are equally critical to unraveling the story of our galaxy's past. These missions will use highly precise measurements of star positions, velocities, and chemical compositions to offer a detailed view of the Milky Way's structure. The data collected will help astronomers reconstruct the galaxy's formation, shedding light on the processes that have influenced its growth and development over billions of years. By understanding the patterns of stellar evolution and star distribution within the galaxy, scientists can piece together a clearer picture of how the Milky Way took shape and continues to evolve. Another crucial advancement comes from the development of space probes, which are designed to collect and analyze cosmic dust, gas, and other interstellar materials. These probes will provide invaluable data about the building blocks of galaxies, offering insights into the processes that drive star formation and the evolution of galaxies themselves. Through this instrumentation, astronomers hope to unravel the mysteries of how galaxies form, evolve, and interact over time, offering new perspectives on the cosmic journey of the universe. The results of these missions and technologies will provide a deeper, more nuanced understanding of the Milky Way and its place in the larger cosmic landscape, ultimately advancing our knowledge of the universe's most fundamental processes. Furthermore, the rapid advancements in computer simulations and artificial intelligence have become indispensable tools in modern astrophysics and cosmology. These sophisticated computational models are enabling researchers to simulate the intricate processes of galactic evolution, testing hypotheses about how galaxies form, grow, and interact across vast stretches of cosmic time. By comparing these simulations with real-world observational data gathered from powerful telescopes and ambitious space missions, scientists are refining their understanding of the universe's complex history. What makes this scientific journey even more remarkable is the global nature of these collaborative efforts. Large-scale sky surveys involving scientists from all corners of the world are playing an increasingly pivotal role in unraveling the mysteries of the cosmos. These initiatives, combining data from a multitude of observation sources, offer a panoramic view of our galaxy and beyond. The upcoming astronomical surveys promise to catalog millions of stars, potentially uncovering hidden structures within the galaxy and providing unprecedented insights into the role of dark matter in the formation of galaxies. The future of galactic archaeology depends on a synergy of cutting-edge telescopes, innovative space probes, and advanced computational methods. When united, these tools will open a window into the very building blocks of galactic formation and evolution, offering us a fascinating glimpse into the cosmic past. They will reveal not only the architectural history of galaxies, but also the intricate interactions that have shaped the universe over billions of years. One of the key elements that underpin our understanding of the universe is the concept of cosmic constants, those fundamental quantities that govern the behavior of all matter and energy. These constants are like the laws of nature, determining the way everything from subatomic particles to massive galaxies interact with one another. Among the most crucial of these constants is the gravitational constant, a number that defines the strength of gravity. This constant determines how objects attract one another, even across the most enormous distances in space. Another critical constant is the speed of light, which defines how fast light can travel through a vacuum. This value is not just a speed limit for light, but also the ultimate speed limit for any form of matter or information in the universe. It is the foundation of Einstein's theory of relativity, shaping our understanding of the fabric of space-time and how time itself behaves. According to relativity, time moves differently depending on the speed and gravitational field of the observer. The speed of light thus is not just a number, but a key that unlocks the mysteries of time, space, and their interwoven relationship. Additionally, there are other constants that define the strength and nature of the fundamental forces of the universe, such as the electromagnetic force and the weak nuclear force. These constants influence phenomena as varied as the way atoms bond to one another, to how stars generate the immense energy required for nuclear fusion. Understanding these constants allows us to explore how the most basic interactions of matter give rise to the complex structures and processes that make up the universe, from stars and galaxies to life itself. The significance of these cosmic constants cannot be overstated. They are, in essence, the instructions that ensure the ingredients of the universe come together in a coherent and predictable manner. Without these constants, the formation of stars, galaxies, and even the processes that allow life to exist would be inconceivable. They act as the scaffolding of reality, enabling the universe to operate in a stable, predictable way. Without them, chaos would reign and the cosmos would be a very different place. However, as we delve deeper into the structure of the cosmos, we are faced with an intriguing possibility. What if these constants are not, in fact, constant? Imagine for a moment that the fundamental rules of the universe are not uniform across space and time. This would imply that the cosmic constants, such as gravity or the speed of light, might change depending on where you are in the universe, or at what point in cosmic history you observe. In other words, the universe might be a place where the rules of the game shift, not just across vast distances, but even across different epochs of time. This notion challenges the very bedrock of modern cosmology. If the constants were to fluctuate, it could radically alter our understanding of how galaxies, stars, and planets form. For instance, imagine a region of the universe where gravity is weaker than it is here on Earth. This could result in galaxies forming in fundamentally different ways, potentially influencing their structure and behavior. Some galaxies might form robustly, while others might struggle to hold together, giving rise to a far more diverse and unpredictable cosmic landscape. Such variations could also have profound implications for the theory of cosmic inflation, the rapid expansion of the universe that occurred just moments after the Big Bang. If the constants fluctuated during this critical period, it would mean that the current models of the universe's early development would need to be radically revised. The possibility that these cosmic constants might not be constant at all raises fundamental questions about the origins of the universe and challenges the concept of a uniform, predictable cosmic evolution. These uncertainties are driving scientists to explore new frameworks and theories, prompting a reevaluation of everything we thought we knew about the universe. Every discovery in this field has the potential to reshape our understanding of the cosmos, underscoring the dynamic and ever-evolving nature of scientific inquiry. This uncertainty is a reminder that the universe is more intricate, more complex, and far more mysterious than we could ever have imagined. What we once believed to be immutable laws might turn out to be more malleable than we ever thought possible. When we think of constants such as the speed of light or Newton's gravitational constant, we are considering the bedrock principles of the universe. These constants form the foundation of our understanding of the cosmos. The speed of light, for instance, is not just a number that describes how fast light travels. It is the ultimate speed limit of the universe, governing the maximum velocity at which energy or information can propagate. This constant dictates the fabric of space-time, ensuring that the universe operates within the boundaries of relativity. The behavior of time itself is shaped by this constant, which allows us to understand how different observers experience time based on their relative motion or gravitational fields. Similarly, Newton's gravitational constant is the cornerstone of gravitational theory. This value determines the strength of the force of gravity between objects. Without it, we would be unable to explain or predict the motion of everything from falling apples to the orbits of distant stars. This constant is essential to our understanding of celestial mechanics and the movement of objects throughout the universe. It is the invisible hand that governs the dance of galaxies and the formation of planets and stars. Together, these constants provide the framework for the laws of physics. They form the underlying rules of the cosmic game, shaping everything from the structure of galaxies to the interactions between individual particles. These constants are the hidden threads weaving together the fabric of the universe, allowing us to study and understand the forces that govern reality itself. Yet, despite their fundamental importance, many questions remain about the true nature of these constants. Why do they have the values they do? What sets the fine structure constant, which governs the strength of electromagnetic interactions at its specific value? Scientists have proposed a range of theories to explain these mysteries, from the possibility of higher dimensions to the suggestion that there is a deeper, more profound order of physics waiting to be discovered. The mystery of why the universe behaves according to these specific laws is one of the greatest challenges in modern physics, and it continues to inspire new lines of inquiry that may one day unlock even deeper insights into the nature of reality itself. The gravitational constant, often seen as a fundamental measure of gravity's strength, remains one of the most perplexing quantities in the universe. Despite its crucial role in shaping the cosmos, it stands as a mystery. Its value appears to be finely tuned, almost as if designed to allow the formation of stars, galaxies, and the very structures that make up our universe. Yet, we are left with profound questions. Why does this constant seem to be so different from other forces of nature? How does it relate to the quantum realm, where the rules of reality are drastically different from the macroscopic world governed by gravity? These questions remain unanswered, leaving scientists grappling with the unknown. As we delve deeper into the nature of gravity, we face a puzzling thought. If gravity is as fundamental as we believe it to be, why does its value seem so distinctly different from other forces like electromagnetism, the strong force, or the weak force? Furthermore, the idea of cosmic inflation, the rapid and vast expansion of the universe in the moments following the Big Bang, adds another layer of complexity to the story. During this early period, the universe grew exponentially, and in this immense expansion, the initial conditions set the stage for the values of the fundamental constants that govern everything. Could the incredibly delicate balance of these constants be one of the reasons the universe evolved in the way it did? And what if, in some distant corner of reality, our universe is not the only one? Some theories suggest that ours might be one of many universes, each with its own unique set of constants, an idea that raises intriguing possibilities about the nature of the multiverse. At its core, the pursuit to understand these cosmic constants is more than just a search for answers. It's a quest to unravel the very fabric of the universe, to comprehend the invisible threads that bind stars, galaxies, and life itself. As our tools and technologies become more sophisticated, we inch closer to unveiling the mysteries hidden within these constants. The implications of such discoveries could be nothing short of groundbreaking, potentially changing everything we thought we knew about the nature of reality. In a sense, understanding these constants is akin to solving a puzzle. Each new piece we discover brings us closer to understanding how the universe works and, more importantly, why it works the way it does. These cosmic constants, such as the speed of light and the gravitational constant, are more than just numbers. They are the fundamental pillars upon which our universe stands. They govern everything from the way light travels across space to the very formation of stars and galaxies. If scientists were to uncover that one or more of these constants can change depending on specific conditions, the implications would be profound. It would challenge our current understanding of the laws of physics, particularly the idea that these constants are fixed and unchanging. Imagine a universe where the forces of nature, like gravity or electromagnetism, weren't constant at all. What if, instead of being uniform across the cosmos, these forces fluctuated depending on the location or time? Such a revelation would force us to rethink the very foundations of theoretical physics. In this new reality, established theories like general relativity and quantum mechanics might require a complete overhaul. We might be on the verge of discovering a unified theory, a framework that seamlessly brings together the forces of nature into a single, elegant description. But there's more to these cosmic constants than just their mathematical properties. Their values also hold the key to understanding why our universe is so perfectly tuned for life. The balance of these constants allows matter to exist, stars to form, and galaxies to evolve. If even the slightest shift in these constants were to occur, it could spell the end of life as we know it. But if we can uncover the deeper connections between these constants, we might be able to answer some of the most profound questions in science. What conditions are necessary for life to exist? And is life possible elsewhere in the cosmos? As scientists continue to investigate the mysteries of cosmic expansion, dark matter, and dark energy, the answers they uncover could drastically reshape our understanding of the universe. Any revelations about the constants that govern the cosmos could provide fresh insights into some of the universe's most enduring mysteries, such as the nature of black holes or the origins of the Big Bang itself. These insights could fuel not only advancements in theoretical physics, but could also change the way we think about space, time, and existence itself. In the end, understanding these fundamental constants might hold the key to unlocking the deepest secrets of the universe, bringing us closer to answering the profound questions that have captivated humanity for centuries. One of the most captivating phenomena in the universe is time dilation. It's a concept that challenges our everyday understanding of time as a constant, unchanging force. Time dilation reveals that time does not pass at the same rate for everyone. It can stretch or contract depending on how fast an object is moving or how close it is to a massive gravitational field. Think of time as a fabric that can bend and stretch under certain conditions. When an object approaches the speed of light, that fabric of time stretches. For someone traveling at high speeds, such as an astronaut zooming through space, time for them slows down compared to someone standing still on Earth. In other words, the faster you go, the slower time moves for you. This isn't just a theoretical construct, it has real-world implications. If an astronaut were to embark on a journey through space, traveling at a significant fraction of the speed of light, they would age more slowly than people on Earth. When they return, they would find that they've aged less than their friends and family, even though the time that has passed for them has been the same. This is one of the most fascinating consequences of time dilation. The faster you move, the more time seems to slow down for you. Gravity, too, plays a critical role in how time works. The stronger the gravitational field, the more time is affected. For instance, near a massive object like a planet, a star, or even a black hole, time behaves differently. The closer an object is to a massive body, the more slowly time moves for it. Imagine standing on the surface of a black hole where gravity is so intense that time itself seems to crawl. If you were to stand far away from the black hole, however, time would pass much faster for you. This warping of time due to gravity is another example of how time is not a universal constant. It is influenced by the objects around it, making time a dynamic, ever-changing phenomenon. These insights into the nature of time have profound implications for how we understand the universe. Time dilation forces us to reconsider our assumptions about time as a fixed, unchanging backdrop to our lives. Instead, we see that time is flexible, malleable, and intimately tied to the fabric of space itself. Time is no longer just a steady, ticking clock. It is a force that can stretch and bend, dictated by the speed at which we move and the gravity around us. This revelation reshapes our understanding of existence. challenging our perceptions and pushing the boundaries of what we thought was possible. Time, it turns out, is not just a measure. It is an experience, shaped by the vast, intricate web of forces that govern the cosmos. Einstein's theory of relativity is the cornerstone of this new understanding of time and space. His revolutionary work shows that time and space are not separate entities, but are intertwined into a single continuum, what we call space-time. According to Einstein, the force of gravity isn't simply a pull between masses, it is the warping of space-time itself. This means that time and space can both be distorted by massive objects, creating the effects we observe as gravity. For astronauts, these effects are particularly pronounced. When moving at high speeds or living in different gravitational fields, time behaves differently. If an astronaut were to travel in a spacecraft moving at a significant fraction of the speed of light, their clock would tick more slowly compared to someone on Earth. The faster they go, the more pronounced this effect becomes. Eventually, they could return to Earth having aged much less than those who stayed behind. This phenomenon, known as time dilation, is not just a theoretical curiosity. It's a real, measurable effect that has been confirmed through experiments involving high-speed particles and precise clocks. It's a testament to the power of relativity and the strange, mind-bending nature of the universe we live in. The influence of gravity is an undeniably profound force that shapes the very fabric of our universe. According to Albert Einstein's groundbreaking theory of general relativity, gravity is not simply a force between objects, as once thought by Sir Isaac Newton, but rather a distortion of space and time itself. In essence, massive objects like planets, stars, and even black holes warp the very structure of space-time around them. This warping means that time, as we understand it, is not a constant for all observers. The closer you are to a massive object, the slower time moves relative to someone farther away from the source of gravity. Take, for instance, the unique case of astronauts aboard the International Space Station, ISS. The ISS orbits the Earth at a height of approximately 400 kilometers, where the gravitational pull is weaker compared to the surface of the planet. As a result, time for astronauts aboard the ISS passes slightly faster than it does for people on Earth. This fascinating difference is an observable manifestation of the concept of time dilation, a core aspect of Einstein's relativity. What seems like an insignificant variation in time can have profound consequences, especially when we consider long-term space travel. For astronauts on interstellar journeys, the passage of time could be markedly different from those remaining on Earth, creating scenarios that challenge our fundamental understanding of reality. One of the most compelling experiments demonstrating time dilation took place here on Earth, involving high-speed particles. Physicists used particle accelerators to create muons, which are unstable subatomic particles that typically decay within microseconds. However, when these particles were accelerated to speeds close to that of light, they appeared to live longer, defying their usual rapid decay. This was because, at these high velocities, time slowed down for the muons relative to observers at rest, a direct consequence of time dilation. Such findings dramatically illustrate how velocity can affect the passage of time in ways that defy our everyday experiences. Another crucial experiment involved atomic clocks, which are among the most accurate timekeeping devices ever created. In one of the most significant tests, two synchronized atomic clocks were set to the same time. One clock remained stationary on Earth, while the other was flown around the world on a commercial airliner. Upon comparing the two clocks after the journey, scientists found that the clock on the plane had experienced slightly less time, just as predicted by Einstein's theory. This experiment confirmed that motion, as well as gravity, has a tangible effect on how we experience time. The clock on the plane moved faster in time relative to the one on Earth, offering concrete evidence of the stretching and contraction of time based on velocity. The effects of time dilation are not confined to experiments conducted on Earth. In the realm of outer space, the effects are even more pronounced. Satellites orbiting Earth provide another real-world example. These satellites, which are equipped with atomic clocks, move at incredibly high speeds and are also affected by a weaker gravitational field compared to the surface of the planet. As a result, their clocks tick at a slightly different rate than those on the ground. This time difference is so precise that the Global Positioning System, GPS, which relies on satellite-based timing to provide accurate navigation data, must account for it in real time. Without these adjustments, GPS coordinates would quickly become inaccurate, demonstrating how deeply time dilation affects our modern technological systems. Each of these experiments reinforces a powerful insight. Time is not a universal constant. Rather, it is a fluid and malleable experience, shaped by the speed at which we travel and the gravitational fields we occupy. This revelation forces us to reconsider the nature of reality itself and to acknowledge that time, as we experience it, is not as straightforward as it once seemed. Our perception of time is not the same for everyone, and it can be stretched, compressed, or altered depending on our motion relative to others and the gravitational forces at play. For future space travelers, time dilation presents both an exciting opportunity and a significant challenge. Imagine, for example, two identical clocks. One remains on Earth, while the other is placed aboard a spacecraft, traveling at a significant fraction of the speed of light. For those on Earth, time proceeds as usual, but for the astronaut aboard the spacecraft, time slows down. This means that while only a few years might pass for the astronaut, many more years could elapse for people on Earth. This difference creates a dramatic disconnect between the experience of time for space travelers and those they leave behind. This discrepancy is more than just a theoretical concept. It has real implications for long-term space missions. As humanity ventures farther into the cosmos, astronauts could find themselves in a situation where their experiences of time diverge from those of their families and loved ones back home. A journey that seems brief for the astronauts could result in decades or even centuries passing for those on Earth. This has deep emotional and social consequences, challenging the very nature of relationships and societal structures. The psychological toll of time dilation is something that must be carefully considered when planning long-duration space missions, as it could dramatically affect the mental health of astronauts and their ability to reintegrate into life on Earth after their journey. On the other hand, time dilation presents exciting opportunities for space exploration. The ability to travel at relativistic speeds, while it poses significant technological hurdles, could allow humanity to explore distant stars and galaxies within a single lifetime. Theoretically, if we could harness advanced propulsion technologies, such as those proposed by relativity, we could reach other star systems in a time frame that would make interstellar travel feasible and realistic. The dream of traveling across the vastness of space may one day become a tangible reality, but only if we can master the principles of time dilation and overcome the technical challenges associated with relativistic travel. Moreover, understanding the dynamics of time dilation could drastically improve how space missions are designed and executed. By accounting for the differences in time passage, space agencies could create mission plans that account for the psychological and social impacts on astronauts, ensuring that they remain mentally and emotionally equipped to handle the challenges of deep space travel. This could also help optimize the reintegration of astronauts upon their return to Earth, where they may find themselves dealing with a world that has aged much more than they have. While time dilation presents challenges, it also opens new doors for humanity's future in space. It transforms what once seemed like insurmountable barriers into exciting new frontiers for exploration. The vast expanses of the universe, once beyond our reach, could one day be within our grasp, thanks in part to our understanding of time's flexibility. The concept of relativistic time travel, closely tied to the theory of relativity, raises intriguing questions that blur the lines between science, philosophy, and practicality. At its core, relativistic time travel suggests that by traveling at speeds close to the speed of light, we could experience time at a rate vastly different from that of stationary observers. This concept forces us to reconsider our understanding of time as a linear, unchanging phenomenon, and challenges us to think of it as a malleable dimension that can bend and stretch. Philosophically, this idea invites deep reflection on the nature of time and existence. If we could travel into the future by moving at incredible speeds, what would that say about the way we experience life, memories, and aging? Could the future become a tangible destination, or would it only serve to highlight the limits of human perception? Such questions are not just theoretical, they have profound implications for how we think about our place in the universe. Moreover, the possibility of traveling through time raises ethical questions that are as complex as the science behind it. If one could alter the course of their own timeline, what moral responsibilities would come with that power? Could we rewrite history, and if so, should we? The paradoxes of time travel, where actions in the past can affect the future, challenge our understanding of causality, fate, and free will. The moral dilemmas posed by such possibilities would need to be carefully considered. However, while relativistic time travel presents fascinating theoretical possibilities, it remains beyond our current technological capabilities. The immense energies and forces required to reach relativistic speeds are far beyond what we can achieve with today's technology. Even if we could somehow reach such speeds, the biological consequences for humans would be staggering. Time dilation would mean returning to an Earth that has aged considerably more than the traveler, potentially leading to isolation and disorientation. In conclusion, the concept of relativistic time travel remains an area of immense intrigue, inspiring both scientific curiosity and philosophical inquiry. While it challenges our understanding of time and reality, it also serves as a reminder of how much we still have to learn about the universe. As we continue to explore the boundaries of space and time, we are constantly reminded that time is not just something that passes. It is a dynamic, flexible dimension that holds the key to unlocking many of the mysteries of the cosmos. The pursuit of this knowledge will undoubtedly continue to shape humanity's journey through the stars.